Perhaps I can. Error indicates unsupported. Right, we would need to use the TypeScript loader. To set that up, how hard would that be? It can't be that hard, can it? Does anybody have I'm really thinking I should be able to find a Webpack config that has TypeScript support.
Yeah, just while you're searching for that Webpack config, I just wanted to circle back to that concept of the distributing of the computation and allowing for that to be included in the unlocking script. I think that's such an innovative, maybe even second only to micropayments in terms of the unique functionality that the network enables, because what it really enables is similar to the original concept of the distribution of labor. It provides that, but in a digital sense, where now, let's just say for the sake of discussion, you have a really complex image analysis software and you're using it to analyze the sky, so you can, it's really complex because it's able to pick up these very distant, faint hues of light that are coming from, millions of light years away, etc. And that's a really complex system, but you can obviously really only be using that at night because the stars aren't visible at night. So essentially that system becomes dormant all through the daylight hours, when maybe you could be repurposing its computational power that is so custom and so specific, but you can repurpose that to some other computational requirements that maybe maybe exist in other parts of the world to analyze really low level things like microbiology. You still need very complex image analysis, but you're using it in a different way.
Yeah, or even just when it's nighttime in some other part of the world. Just now it gets data from some other source.
Yeah, I just absolutely love that use case because I think it makes us a more globally connected network when we can share our problems and our burdens onto the systems that are most enabled to solve that. And it's similar to how the Bitcoin network itself has a sort of a problem, which is how do we verify all of these transactions, and that gets to be offloaded, so to speak, onto the nodes who are acting as this validating network for the entire network.
Just going to install this Babel preset. Maybe that will save us. Does anybody have any thoughts from the developer side about how to get this TypeScript thing going? Maybe I just need to install TypeScript or something. Because I think when we try to implement the script template interface, right, we'll need to actually make use of TypeScript within this project. So I added a loader for Babel loader for the TypeScript files. And I have kind of added the Babel preset for TypeScript. I don't think we need decorators or class properties, but we may need TS loader, that probably sounds like the right thing. I think we'll need that. TS loader. So that would probably. And then I should change the loader for TypeScript files to actually make reference to the TS loader, perhaps. Aha, got a different error. Okay, and then I'll take the TS config and actually copy it. So what I'm doing is just grabbing some code from a TypeScript project. What I want to do is, and if you guys aren't able to follow along, I will publish this code, or I'll make it available. But just trying to get my environment to cooperate. And I apologize for not having this kind of ready to roll right beforehand. But okay, now I have a TS config and I should be able to okay. I don't know if I'm going to be able to make this work using this code path. So essentially the concern is that implementing the interface for the script template would require us to have a TypeScript capable environment. And this simple React app that I pulled down did not implement TypeScript, and therefore, implementing this multiplication template will prove difficult. We can move to another environment that has that capability, such as TS Node, or we can attempt to let me actually look at another.
I think that I figure out how to set up it.
Okay.
I managed to push it on the branch TS on the simple React app.
Oh, you have a okay, very cool.
I got the access from you previously. So, sorry.
Okay. Yeah, no, that's great. Let me just oh wait, I can just check out. All right, so yeah, everybody can just see git pull.
I didn't commit this multiplication template and didn't commit.
Yeah, we'll go through that together. Yeah, that'll be good. I'm just going to remove this from my. Oh, I see. So I can maybe just save that.
The landscape of blockchain development is complex, particularly with the core BSV libraries, where scattered forks and alternatives have created a jumble of options to pick from. To tackle this, we've unified them into a new library, ensuring developers have an official SDK which is easy to use, backwards compatible, stable, and performant. In software development, stagnation means falling behind. The BSV library had started to deteriorate with dependency rot and outdated functionality due to the shutdown of the wallet company which maintained it. By thoroughly revising the codebase, we've streamlined it to be more clean, functional, and formidable, now supporting an SPV approach to transaction construction and propagation. External dependencies can slow down maintenance and complicate updates. The SDK was built from the ground up with no dependencies, making it lighter, faster, and a comprehensive educational opportunity for developers who want to go deep on the details. This effort was made in order to ensure a stable, well-maintained core library for applications built on BSV now and into the future. Our ambitions extend beyond the JavaScript ecosystem. We are applying the same principles to develop officially maintained libraries for Python and Go. These tools are not just additions, they're part of a cohesive strategy to provide developers with robust, maintained, and standardized resources that meet the demands of scalable blockchain application development. The BSV Library project is more than an update. It's a strategic overhaul to prepare for future challenges by providing a stable foundation for innovation. We're doing the groundwork so developers can focus on creating revolutionary applications. Join us as we pioneer a more efficient, secure, and innovative ecosystem. The BSV Library project, building the foundation for tomorrow's blockchain applications.
All right. Welcome back, everyone, for our afternoon session. I am Brett Banfi, your host, Manifestable, and I want to give a welcome to our viewers at home. We will have an update in this next session on behalf of the BSV Technical Standards Committee from Angus Brown of Minute Money. Angus, welcome.
Thanks, everybody. Just checking you can hear me here and online. All good, looking good. Thank you. I'm the guy who has to bring you all back from lunch and nice networking conversations and that. So apologies for dragging you away, but let me give you a little bit of an update here on the role and objectives of the Technical Standards Committee. I know the perspective you always take is, okay, so what's in it for me? What am I going to get out of the next couple of minutes? Are you going to show me some code? Are you going to give me an insight into how to, write better code or libraries I can use? So I thought this little intro clip was actually very appropriate. See if I can get, what I want to do today is just take a couple of minutes to give you some insight into what the Technical Standards Committee does and why that has got some value to you. Now, you think sort of standards, what value are standards there? But I'm hoping at the end of this, you'll see that there is some value in the confidence you can take in the tools and techniques and libraries and things that you have. So that's our objective as the Standards Committee, is to make sure that that you all have confidence in the tools and everything that you get, and that they are of high quality. So just quickly run through it. What do we strive towards? What do standards do? Who are the stakeholders? How does the Technical Standards Committee, the TSC, fit into the rest of the BSV ecosystem? And basically, just to say, where was this born from? The TSC actually started from a workshop amongst various BSV ecosystem participants. A couple of years back, we were sort of gathered a couple of people together from different wallets, different mining pools, and different groups to say, we are struggling with interoperability. We've got some things that need to be improved, and that would be better if we did them together. And so we need an open forum, an open table to have these discussions. And that turned itself into the Standards Committee. The goal of it is to achieve interoperability. Now, I think, well, I'm building a business, I've got my project, I'm working on this. What do I really need from interoperability? Well, I'm hoping at the end of this quick presentation, you'll get a sense of the importance of interoperability and standards. So one of the elements that we take in this approach is not a top-down approach. We don't decide what standards the industry needs to have. It's a bottom-up, market-driven, industry-driven approach to things. Is we get standards suggested to us, very simply. We try and make sure that standard is developed into a well-governed and appropriate and useful standard, and those are then published. We don't enforce standards. It's not our role to do that. But we encourage people to use standards that are out there. We'll also refine standards if they need to be refined. It's a living world out there. Things change. From the first standards that were put out there, such as Paymail and Direct Payment Protocol and even Merkle Proof, there have been some improvements and changes to the system, and we need to take account of that. So all of the standards are dynamic living standards, like pretty much everything in the code world today. What we need, and why we're here, is we need your participation. You are the consumers of the product that the TSC creates. You use those standards, etc. So be good consumers. Actually participate, engage, lean into it, see what you can do. Tell us what we should be doing better. And then as the committee and as the group that is developing and building on these standards, so we will actually deliver a better product for you. So that's my request from you, is have a look at the standards and actively participate. And maybe a little bit later, you'll see just how you do that. Step back to standards. Standard. It sounds such a boring word. Isn't it like the most bland, boring thing? Does anyone want to be standard in their lives? I don't think you got up in the morning wanting to be like that. But there is a need for this. So what does it actually mean? Standards are used for communication. So you communicate through having a standard syntax and language. That's just how we use it in our day-to-day lives. You can actually think about the probably 100 odd standards that go into being able to have a meeting like this today. Being able to communicate like this, being able to broadcast to the viewers online, to being able to communicate through a microphone to everybody here needs dozens of standards. But they disappear. They go into the background. And that's actually what's important. They must go into the background, but they're still needed. So standards, are including things like the meter. What is a meter? And is a meter the same as a yard, or what's the difference? And is a meter the same in France as it is in Japan? And that's quite an important thing when you're trying to do, pretty much anything that is related to research, industry, etc. So a meter is a standard that is out there, and all of the other things that you think of then from that volume, the size of the glass of wine that you'll be able to buy. That's a standard size in a standard bottle, which enables a factory to produce it in a standard way at a price that you can afford. So that's where standards have come in. They're necessary for measure, dictionary, rules of grammar. I'm sure we all had great fun learning all the rules of grammar. English is my home language and is a complicated one with lots of different elements to it. I was also at school learning other languages and having to learn how they use dictionaries and the rules of grammar. And I could do that through tools such as standards to be able to learn from it. And then the simple thing that I always go back to, you fly here from another country, but you're still able to plug your laptop in and receive electricity. You might need a different plug point. The adapter might be different, but at least you've got voltage that works in a standard way. You're not dealing with DC out the wall. Those are some of the things that are standards. So what happens if you don't have standards? Basically, how do you know when you need a standard? Is often after the fact, when you're in some sort of a trouble and things don't work very well. So one of the oldest stories around this is actually the story of the Tower of Babel, where they were the story of the city and the tower, where everybody was speaking a different language. And because of that, they could not construct this tower. They were trying to build a tower, and you couldn't, because nobody could actually communicate with each other. It's a very, very old story, but it says a lot at the deep level here as well. The picture on the top left is the Mars Climate Orbiter, which was a $75 million project, if I remember correctly, that catastrophically failed because the one team that was building it was working in centimeters and inches, and the other team that was manufacturing it was working in millimeters. It's like such an obvious problem. How could scientists and engineers make such a crazy mistake? But it came into simple. It's just numbers moving between, but those numbers were out. Obviously, it's a badly run project, but still, the root cause was a misinterpretation of standards across that. And that catastrophically failed. Got into space, got to Mars, and sort of completely useless. Did not work. Throw it away. We've hopefully learned a bit from that. So that's one example that I think is also quite spectacular. Then, of course, you end up with competing standards, because you always think there's always one standard for something. You know, it'd be really nice if the world had one standard, but often there are standards that fight with each other. So I'm dating myself nicely with a picture of the VHS and Betamax. So checking who's awake here. Who ever had a VHS or Betamax in their house? Okay, you're dating yourself, audience. I like that. Okay. So online, I'm sure there's a couple as well. There was this debate, and it was different in certain countries, but you always had this thing. Now, you wanted to get a video from somebody, but they had a Betamax and you had a VHS. So now you're stuck. You can't watch it. And which one's better? In the end, everyone would have a view. And actually, in the end, there was actually a different technology, which was better than both of those, but actually didn't go anywhere at all because VHS and Betamax did good marketing. So they're two giant marketing companies fighting with each other. And in the end, who won? VHS. No, the DVD won. So this was all supplanted, all became irrelevant when the DVD came out and actually passed all of this altogether. So this is a good story about standards fight with each other and then become irrelevant. That also happens in the real world. And then, of course, my most fun one is trying to figure out what adapter I need for this device. And does this adapter fit into that? It's become a lot better. And I think the EU has put out standards now that even Apple devices must start using the USB-C adapter. And USB-C has become much more of a de facto standards, even for power and that. And it's got some good technical advantages. But for a long time, you had to go and figure out, does this adapter go that way around or that way around? And you know the rule is you've got to do it 3 times before you can figure out which way around it goes. So that's because we had different standards. So it happens, and it's driven also by market forces. So a market force will push a particular standard. So those are just some of the examples. It's always fun to look at how a standard doesn't work, but it's not so fun at the time because it's got an impact on people. So that's what we at the TSC is trying to do, is trying to improve and reduce the impact on yourselves. So technical examples where you all use standards yourself is things like coding syntax. I presume 90% of the people in the room are coders, maybe more. You'll all have learned certain style guides, syntaxes, taxonomies that you're supposed to use, and that the better you use them, the better the quality of the code and the outcome you get. So those are standards that are actually just applied in what you do. There are data structure standards. I'm very familiar with the banking standards, such as ISO 222, which is now pretty much the de facto standard in any much of the financial world. You're trying to do financial messages, it has to fit into that format. People are getting certified in those sort of standards. You've got the SWIFT, a very old system, sort of like, you know, pre-Satoshi, there was SWIFT. Post-Satoshi, now we can actually go to something a little more useful. But that's still used by the banking systems out there. Those empty messages are used to carry financial information. In the KYC world, the Know Your Customer world, there are standards out there now. The IVMS standard is becoming probably quite a useful standard for how to carry information about customer data and customer records for when you need to pass that information around. There's patterns, there's APIs, how to publish an API. All of you who consume APIs need that standard, which is a standard way to interact with that third-party system, or you're publishing APIs that allow other people to consume your code. So those are all elements that are actually in place at the moment that we all use and need. So stepping now from the conceptual world of standards into the world of the TSC itself. So the TSC is a committee that basically helps to govern the production of standards in the BSV ecosystem. So we receive applications, I'll take you to the life cycle in a minute, and then we produce standards. But where do these come from? What's the origin point on them? And also wanted to here make it clear that it isn't coming from the TSC. That arrow goes this way. It doesn't go that way. We don't tell the community which standards you need to be adopting or originating. It comes in from the left here. So there's something called the BRCs, the Bitcoin Request for Comment, which is very much a place for ideas. And people just need to clarify that. The TSC doesn't run the BSV BRCs at all. The BRCs are a place to put ideas, be creative. I think there's more than 50 ideas there at the moment. So here's a piece of code that I think is useful. Here's an idea that I think is useful. Let's see if people can pile on. It's very informal. It's very easy ability to add on comments, suggest, bounce it around, and turn it into something useful. Like any ideas, some of them will be useful, some of them won't. We also don't know when they'll be useful. Don't know at what point a good idea is not ready now, but might well be useful in 6 months' time, or a year's time, or 2 years' time. So that's one of the source of ideas or standards, comes out of the BRCs. And a BRC is also a good indicator of whether people find this at all interesting, or whether this is something that's completely arcane and relevant only to 3 people in the corner, and the rest of us don't care, which is fine. But if you're seeing a BRC that actually has some traction and some excitement around it, and people are commenting and agreeing with it, then it's an indicator that this is a problem the community is struggling with and needs solved, and particularly needs solving for more than one party. So standards are also, all about how do several parties get together and discuss things together. You can use discourse or Reddit, you can have conversations that way, but in the end, this standard needs to evolve a little bit. That's what it goes over here. Another one is the stream leads from the BSVA. The BSV Association can also generate standards ideas. They're working, Teranode, Arc, Bucks, all of these ideas are coming out. The teams inside there are going, there's something that if it was standardized and put out there would be so much better, would help the BSV ecosystem. So they come up with ideas and they put ideas here as well. There's one that we're actually working on at the moment that came out of the BSV Association. Don't know if I can mention at the moment. I think Darren would be very keen if I was to push it forward a little bit more. But there's ones that come out of here from the ecosystem that we want to just push through. There are BSV devs. You don't have to be employed by the BSV Association in order to be a BSV developer. You will be coming up with ideas. Everybody in all these different companies in this room are coming up with ideas. And those ideas are perfectly valid, good ideas and suggestions for standards. There's businesses, so it's not just the developers, but businesses as well. Standards don't only work for technical areas. One of the standards that we've had for a little while is the travel rule standard. The travel rule is not a very technical standard. It's more a process standard about how do businesses communicate, particularly wallets that are regulatory compliant, how do they communicate information about their customers backwards and forwards, which is necessary for the travel rule. Travel rule is the international rule that governs, the KYC information that must flow with payments. So it's a business-orientated standard, actually. It's not terribly technical, but it comes out of the business need to actually process transactions between wallets. And then, of course, there are the TSC members themselves. There's, I think, about 10 of us on the committee. We also come up with ideas. And sometimes those ideas we throw into the pool as well. No special favor for the TSC. It's got to run through the same process as everybody else. So this is just an illustration to you of the many different places that standards and ideas for standards can originate from. What happens next? Classic life cycle slide. I'm pretty sure nobody can read the text on that except the high level. That's fine. I'm close enough to it. And I'm actually not going to get into the detail of that because it's really simple. There is an email or a submission of a standard request. Basically, there's a template that we use that says, what's the business need? What's the problem you're trying to solve? Why is a standard needed? And what is the suggestion around it? It's not just a problem statement. we also look for a solution statement as well. Like, how is this going to be solved? And a benefit statement. Who benefits from this particular solution? And that's pretty much it. It doesn't have to be very detailed. I don't need code in there. It's just, this is how a submission is created. We review it. We look at it on a set of criteria inside the committee. And once the committee has looked at it and said, yes, it meets our standards, it meets our criteria for going forward, and those are transparent and steady criteria that are used for all standard submissions, we then go accepting the standard, and then we form a working group. A working group is basically just a small group of people who are technical experts who need to be involved with a further articulation of that standard. Sometimes it's the standards originator, the guy who came up with the idea. That's often somebody who quite needs to be involved with the further fleshing out of it, but it's often other people who have something to contribute. From the ecosystem, sometimes from the BSV Association, but it's a group of people who can then take this idea forward. And quite often, those working group people have already been involved in the BRC process. They're already on discourse talking about it and debating something. Maybe they're talking about it in a bar. That working group is often like pre-formed, but that's fine. We then just agree, who's the working group? Put that team together. We allocate a sponsor, one of the TSC members who keeps an eye on things, make sure that it goes along. And then the working group starts having a conversation. How long does that take? Sometimes it can take months because people are busy and they haven't got time to do it. Sometimes it can be urgent and it can be weeks where people can form the working group, talk about it, and maybe they already have the solution pretty much agreed and they will get to the end of that process. We don't actively project manage that outcome. So it's not our responsibility to say this standard has to be out the gate within 6 months. Be nice, I guess, for everybody if that was the case, but we're not in control of the working group members. Those working group members are participating voluntarily. They're giving their time, energy to try and actually find a solution. The more there's a business need, the more they will benefit from the standard, the more time and energy they put in. This is natural dynamics, natural economics in here. That working group will then come up and document a standard. We expect it to be on Word. We'd like it to have sample code. We'd like to have a reference implementation. Not actually necessary. Sample code is sometimes quite useful, particularly for a technical element to be assessed. And then that will go back to the TSC. The TSC will say, yep, we're happy. It seems to be meeting the business needs. The process of conversation in the working group was sound. The debate was solid, the discussion. Not everybody has to agree, but the way the conversation was handled was appropriately, the views were aired and opinions were discussed and debated. So we also make sure that the process inside the working group is well governed and well run. Because, sometimes people can throw bricks at each other as well, particularly on anonymous forums or those sort of areas. So we try to facilitate that. Then at the end, we publish it for public comment. People will put in comments, suggestions, etc. We listen to those public comments. That can take a couple of weeks or a couple of months to wait for people to come in and comment. If there's suggestions that we need to listen to, that the working group feels there's improvements made it, we make the improvements. And then it goes out and is actually published. We used to have it that it was a draft standard, and then it went to a final standard. Practically, if it's published, it's a standard. Whether you want to use it or not is entirely up to the industry. So there isn't any status that is actually conferred onto a standard once it's been there 6 months or it's got some final status. It's a document that people must use. It's sample code and reference implementation people must use. It's really quite simple. So these are the committee members. Don't want to list them. You can look at the TSC website as part of the BSV Association. You can see their CVs there. They're all volunteers. Some of them, a very small number, come from the BSV Association. Mostly they're independent from the BSV Association. And the criteria that we use is some level of technical experience. some familiarity with the need for standards and how standards work, experience it working at an industry level. So, if you understand how industries work and how sort of these NGOs or associations work is also quite valuable. And they come from a range of backgrounds. Some people are deep technical, some people are cryptographers, mathematicians, some people are business people, some people are project managers. There's different experiences that come through from that. And we select the TSC members to give a range of skills and experiences in that. But they are volunteers, and they basically just wish the BSV ecosystem would grow and develop, and this is their contribution to that. The element that this all leads to is an outcome that you can take some assurance in. That's what we want to see. You see those logos of ISO, IEEE, W3C, those sort of logos, ANSI. Once there's a stamp like that on a standard or a document or a plug that's got an ISO standard on it, you feel confident you can use it, it's safe to use. And we try and assure that through the process of governance. We have quite strict structures about how do we take on things, how do we deal with things. It sounds a bit sort of academic, but there's real important reasons why we approach it from a strong governance perspective. It's to make sure the outcome you can use is of high quality. So we want to make sure that that it's open, that it's not just a cabal of one person's view or one particular approach, that actually multiple views are heard, because technical debate is important. And disagreement is also important because it allows a better outcome. And in the end, maybe one person, says this isn't how it should be done, but we try and make sure that there is good, solid debate on the technical aspect. We also have an issue about IP. And this is because you might not be aware of it, but there are IP trolls out there. When you come up with an idea, you come up with something, you think you've got a great idea, you put it out there, and suddenly it's suggested. Watch for other people who might be just deciding to patent your process, patent your code, patent your ideas, and suddenly you're hostage to them, and them suddenly having to have some commercial agreement with them when it's actually all of your work. Or three people getting together and debating something and discussing it. Now you've got to have a fight with somebody. So we have mechanisms in place with NDAs and IP to protect the IP of the people participating, to make sure that that's in there, and also to protect the IP of the product that comes out, that it is in a clean state, that is actually usable by everybody. So it sounds legal and boring, but it's there to protect everybody in the process and to protect everybody using a standard, that they're not going to get IP claims or abuse that way. We also try to be pragmatic and transparent. I think we still have a long way to go. I'm very happy to say, very honest to say that we haven't done as many standards as we want to. Some of the standards are still a bit outdated, particularly with Teranode coming along and all of the new overlay networks that you'll be hearing about, you have heard today and will hear about more this afternoon, that we need to update quite a few of those. And we will. We haven't, I think, got as much engagement with the community, which is why I'm here to say, lean in, go onto the BRCs, come up with ideas, suggest it to us, tell us where we can be more helpful on that. So I appreciate that. So that's part of the transparency, is also sort of owning up where we haven't done enough and where we want to do more. And obviously the last part is reference implementations. That's what you all want to see. Show me the code. James actually did a great presentation about this. You can see the webinars about 8 months ago that there was a good webinar produced. You can look for it on the website. And that's really just, we're trying to get to the point with our reference implementations for all standards that you can use. And we'd also like to see that many of the products that are being created by various people in the ecosystem, TAAL, GorillaBus, nChain, everybody out there, the BSV Association, that all of those products are also aligned to standards. That's what we'd like to see. In a good ecosystem, people are using standards and people are producing standards. So that's where we'd like to get to. We still have some way to go. So this is actually, we've been running this for about 3-4 years now, but it's still actually in its early days. And that's it. Thank you. Do you want to take any questions? Or how are we doing?
Yeah. Were there any questions here? For Angus? Yeah. We have Ken Sato. Sato Sama.
Hi, thank you for the presentation. If your company has some particular technology for, if you have a patent for particular technology and then they want to do for the standard for that, how this process gonna affect? I mean,
That's a great idea, a great comment. And the question is, just in case anyone didn't hear it, if you want to submit a standard, but you think that you've got IP that you want to put into the standard, what's your process? And it happens because most people think they've got a great idea and they own the IP and it's going to be theirs and they're going to get rich. You just need to be careful about how you do that, and our process takes care of that. So when you engage with the standard, we analyze the IP, pre-existing IP that's coming into the standard. We'll have a discussion with anybody bringing their IP in, and we make sure that we cover that. So pre-existing IP is protected because of the process that we use. So.
All right. Well, thank you so much, Angus. And next up, we have a presentation. Please welcome Thomas Moretti and Mike Smolinski from nChain.
All right. Hello, everyone. So Thomas Moretti, head of product at nChain, joined here today by Mike Smolinski from our team that is the product manager for PSP, or Product Suite Platform. We'll go into the detail in a bit. So the session today is generally to show the direction that nChain is taking about its products across the board, not just the one that you will see today. I will have also the opportunity to do another session on identity during the next 3 days, where we will explain you some of the newest concepts and how we leverage BSV generally to add value to our product, not to promote directly BSV, because the enterprise looks for the value of blockchain, not the hassle. So we'll get into that aspect of the philosophy and how we integrate BSV into our product, starting with the product suite platform. So Mike.
Okay. All right, so yeah, my name's Michael Smolinski. I'm a technical product lead at nChain. So I've been working with our team on this product for about 9 months now. We're pretty excited to unveil it today. So you guys are the first ones to see this product. So yeah, I work in the products team at nChain. We're responsible for the new products that are coming out and also the developer tools that we're building primarily for commercialization with enterprises, government organizations, and also startups. So we've got all these great products that are coming out, like Identity, Sign, and a few others that we're going to show to you today. And how the product suite platform came about is that we started realizing that part of the problem with our industry is adoption. And we can have all of these great products, but if it's difficult for enterprises and government organizations to start using them, something that they're familiar with, and also the challenges that we have in our industry with Web3, then we're not even going to get over the line. So this is the purpose of what we call PSP, the product suite platform. So can I do this together? So I don't point it this way. I've been told I've got to do it that way. Yes. So what is PSP? So it's a platform for supporting the development, deployment, and installation of Web3 infrastructure and applications in an easy to use and simplified manner. So what problem are we addressing? So I've actually been working in this space for quite some time before even I joined nChain, and I was a developer, a solution architect, and now I work in products. And working in the blockchain ecosystem is quite difficult if you're going to build applications to the real intent of what blockchain is trying to realize to our world. And just to give you a snapshot, there are 27 million developers in the world. But in the ecosystem of blockchain, not just BSV, there's 20,000 developers. And only one of those blockchains, the leading one, has only 1,000 developers. And so what does this mean? So there's a skill gap. So when enterprises or government organizations come to look at blockchain products and tools, etc., they discover that there's all these new kind of innovative tools and programs to use, and they don't usually have the skills in-house. And we'll discuss that in a moment. It's a fragmented system, so you've got all these different blockchain ecosystems building different things. It's all over the place. And it's quite complex, actually. If you're building a Web3 application right, where it's quite distributed and removing intermediaries, it's quite complex to get that set up. So, diving into the problem a little bit more, giving you a typical example of Web3 development. So by the way, when we talk about Web3, it's a bit of a buzzword in the industry. But at nChain, we believe Web3 is about data sovereignty and digital sovereignty so that the end user can take the data with them across applications. And also digital sovereignty that like enterprises and government organizations can hold their data within their own domain. And that goes quite against Web 2 world, where you have like the Googles of the world and Facebook, etc., which have software as a service, and they have everybody's data commingled together in one centralized place. And the other factor of Web3 that we believe in is removing intermediaries so that organizations can interact with each other in a direct manner. So to achieve that goal is quite difficult. And to take you through the typical problem that a Web3 developer has to think about, they need to create smart contract transactions, pay transaction fees, manage synchronization of data between parties while keeping the information private and secure. And that's quite complex to do. This typically requires a new type of architectural design and necessary skills, creating a lot of inherent development complexities. And this obviously results in a development life cycle that is very extended and takes a lot of effort to do. And this scares away most enterprises and government organizations. And just another snippet, like with blockchain transactions, it's quite easy for a startup if they want to get some crypto and then pay for their application to work. But for most enterprises, if they want to get some crypto, they have to go to exchange and do KYC. And a company can only get KYC onboarded if all the shareholders that hold 20% more of the equity in that business give out all their passports and everything else. And that scares away most enterprises. So they're like, why do I have to have crypto to run this application? So we're addressing all those points. So how does PSP solve this problem? So it's a one-stop shop for building these Web3 applications made really simple. So the point is that you don't need to upskill as an organization. You can use your existing skills that you have. And also it has all the documentation there. And it's very easy and seamless to get through the steps you need to build your application. So we remove the complexity. We provide unparalleled flexibility in deployment. So what that means actually, so you'll see a demonstration of the platform in a moment, but you can deploy your application very seamlessly on our servers if you want to get started. None of the data is commingled with other data. You have your private your own independent domain. But if you want to go a step further, you can actually seamlessly deploy it on your own server. So either in your private cloud or on your own premise infrastructure. And we want to make that super easy at a point of a click to go through that process. And also in the platform, you'll see in a moment when we demo it, you can just click around, there's demos and use cases and documentation, all there at your fingertips. Okay, so in a short moment, we're going to show you the demo, but this is basically the simple flow here. You come along to the platform, you can easily register. It's a few clicks and you just confirm your email. Once you sign in, then you have access to the whole product suite. You can browse each of the different products that we've got available. And then you choose which ones you want to install. So some of them are, like my colleague Thomas will show in a moment, some of them are quite high level products. So they have everything all together with all the UI and everything else. And others are more low level building blocks. And so you can then mix these building blocks together to form the application that you want. And then you deploy it into an environment. So at the moment with this first version, you can deploy it into our sandbox environment. But the way you deploy it into the sandbox environment is exactly the way you'll deploy it into your private cloud or onto your on-premise servers. Okay, so to sum up, it's a simplified developer experience. So it's very easy to use, just point and click. You use your existing skills that you would have in an enterprise with using APIs, no new programming languages that you have to learn. It's rapid and flexible to do the deployments that I've tried to emphasize on different, on our servers or on your servers or in your private cloud. And the final point is around data sovereignty and digital sovereignty, that the end users can keep their data to themselves and move it across applications. And likewise, organizations can keep their data within their data centers, within their country, rather than in different countries and mixed around the world. So we're going to do a demo. This is going to be a bit challenging because I don't have my laptop here just to set up my colleagues at the back. So Leonard, can you just start? Okay, you have, cool. I didn't see what he was doing, but like you can just type in nChainplatform.com and then you'll come to this screen here. So it's actually live right now. So anybody in this audience can go to nChainplatform.com and you can see exactly what we're seeing here and play with all the demos, and then you can register as well and start deploying the different components. So yeah, once you come to the platform, so he's not signed in, so it's got sign in button up at the top right, don't click it yet. So what you'll see here is the range of products that we have available at this moment, just on launch. But we've got quite a few others that are coming in the pipeline. As you can see, we've got a one called event. That's quite simple. That's just putting data onto the blockchain. We've got the sign product, which Thomas is going to demonstrate after I finish speaking. And then we've got identity and asset coming soon. So from this dashboard page, you can go to use cases. Can you click on that? So here it is. This page is primarily for the decision makers in an organization, just to have a look and understand each different product. What are their use cases? Why are they valuable? So you got event, sign, identity at the moment. And if you scroll down a bit, oh yeah. Yeah, so then like, for example, event, you can click on the demo button, please. So we haven't even registered or anything right now. We've just gone straight to the web page, and then you can start playing with a demo that like easily shows what event does. Okay, so what this is doing is it's drawing a lucky number of 1. That's quite good. And then if you click view on blockchain, you can see right now the transaction that was generated on the BSV blockchain. Obviously, it'll take a few minutes to confirm. Thank you very much, Leonard. Go back to the next screen. And if we go back to the platform dashboard. Okay, cool.
Just a point to add. So because we target a lot enterprises as well, we've got two personas that are really standing out. The decision makers, which will look for the value in the products. They will care less about how it works, more about what is it bringing to me and to my company. And we expect, or most of the time, once those decision makers have an idea and they say, okay, this looks good, this does, or this is going to add value to my solution, to my service, then they will jump and ask also their developers, okay, look into the more technical detail of it. So this platform needs to address both those audiences. You need to show the value, but you also need to explain to the more technical people how it works. Today, we've got probably a mix of the two. So you should find a clear understanding about how it works or what is it bringing to you.
All right,
And the demo, effectively, the demos fit that first category of giving you a value, giving you the value. What is blockchain, or what is this product going to add?
So each of the components and products have a number of demos, so you can see the different flavors how it works. All right. So you can then register. Leonard, can you just show the button for registering? Just show that's a very simple one step to do that. Start for free. So you fill in this. Obviously, Leonard's already done that before. So can you sign in for us, please, Leonard? So you don't need to pull out your credit card at all. That's my Kiwi accent coming out. You don't need to pull out your credit card at all. You get to use the whole platform for free initially. So you can trial any of the products. Initially, we've got them for 10 days because the platform's just launched today. So we just want to test some of the load. But in the next few days, you'll be able to trial the products for 30 days. And if you want to keep using them, just as a form to fill out, saying, oh, can you just extend my trial? And we can just do that behind the scenes and flick a button to make that happen. Okay, so Leonard's signed in at the moment. So if you can go to the sign product. Okay, so what we're going to do right now is just show you the simple steps of installing a particular component. So what we're going to do here is he's going to fill out the details, give it a name, and then when he clicks deploy, it's actually going to install all the components that make up this product into a self-contained independent area. Okay, so you started doing that, great. So while that's happening, so it can take a few minutes because it's doing a lot of things in the background. If you just go to the event product, so we've got one that's already installed. So you can see at the top, okay, yeah, it says you've got a 10 days trial period remaining. So we installed that one today. So he's clicked on show the details of it. Actually, if you go back to the dashboard, so when you start actually pulling out your credit card and paying for these products, you can actually have as many different instances of the product that you want. The reason why you may want that, you may want one for your development environment, one for your test environment, and one for production, or maybe you got a number of applications and they're using multiple instances of that product. So can you click on the details again, please, Leonard? Okay, so once one of these products is installed, then you can configure them. And so depending upon how complex the product is, they'll have more kind of fields to configure the product. But we do try to keep it quite simple by not adding too many fields. So here you can see event. So event doesn't have any UI. It's very much an API for developers to build something in front of. So most developers will be quite familiar with this. You have an API endpoint, so you can connect your own application you're building to that endpoint. You obviously have the API key, so that's the secret to be able to access the endpoint. And then if you click on the external link, if you can, Leonard. So this is what, like most developers will use for this, but this is what we call Swagger. So this is basically those API endpoints. So we've installed this product, it's running. You could click on try it out. We're not going to do it right now because you need to upload a file and everything else, but you could click that and click the execute button, and then you'll see a transaction written against the blockchain. And the other thing you can do when you configure the product, you can decide whether to have the mainnet blockchain, the testnet blockchain, or even a simulated blockchain, so nothing gets written out to the outside world. And many organizations actually want that because they want to keep, you know, when they're developing everything quite private until they're ready to go public. Okay, can we go back to the dashboard? Okay, has Sign finished installing it? Okay, yeah, it's done. So you've done Hello Sign. So can you just click on that one for a moment and we can see. Okay, and there you can see it's been installed. And just the last thing to go through, so can you click on the documentation link down the bottom? So we're still building this out, but if you click on nChain event, for example, so each product has quite comprehensive documentation, and we're building this out every day with more examples. And we really want to make the experience like very top notch so that everybody knows step by step what they need to do, and there's a lot of help and assistance. So I think I've rambled on enough. Do you want to, I'll give it over to you, Thomas, to go through Sign.
Yep, cool. Thank you. So if we can get back the slide. So before we get to the demo, I'm just going to do a bit of a ramble on the product itself. So what is Sign? So what is nChain Sign? So it's a solution that allows you to actually sign with make digital signatures that are tamper-proof, secure, and as a transparent verification. One of the two things that when we were talking about the product we should be doing this year, we wanted one, that the product is end-to-end. So it's not just about writing to the chain, it's about also giving all the tools so that somebody can actually verify what has been written. And that means in the case of Sign, maybe an auditor that wants to verify that the document was signed properly, whether it's to check that the subjects or the people were correct, or that the document has not been modified. So providing all the tools, all the features end-to-end is the first point. The second one is tamper-proof. This one obviously is leveraged by the fact that we use a blockchain. But again, here, one of the things that we do when we build our product is we do not put forward the fact that it's using blockchain. Blockchain comes as a benefit of using the solution and adds value to the solution that we provide. So even today, when I'm going to show you Sign, you will see that we are not talking about the blockchain. We're not saying, oh, it's because the blockchain. We just say, okay, here's the user experience, and yet behind the scene, blockchain is being used. Obviously, for this audience, I will tell you a bit more where the blockchain is used for Sign. So what do we call self-sovereign signature? Before I get into this, talk today about what do you use to sign document as of today. Most of you will say probably DocuSign, because that's the standard, or PandaDoc, or maybe an equivalent a bit less known, but most of the time you would use DocuSign. So, sorry? Or this. Or a pen and paper, but let's say in a digital form, yeah, probably one of those solutions. One of the inherent problem with this solution, Mike mentioned it earlier, is that then you have an intermediary to make it happen. If you wanted to have a solution that lets you control the flow of how the document is signed and then have provable stamps that this has happened, then the only way to do it is probably through DocuSign with this intermediary that you don't necessarily always want in the middle. So we say, okay, would there be a way for a truly decentralized or Web3 application to do document signature? And that's how the journey started for it. So the main challenge, I explained a few by giving this speech already, but lack of transparency, the document storage, all of that is done in the premise or in the control of whoever is providing you the service. What if you were able to do the same thing feature-wise as a document, as a DocuSign and the like, but still keep that in control of your organization, not having to rely on an external partner, but get to the same outcome. Well, that was one of the things we were trying to achieve with it. And obviously the cherry on the cake is the fact that you would be able to provide that proof that somebody signed externally to an auditor without having to overshare your solution just by leveraging the chain. So this is pushing a bit that story a bit. nChain sign works in two ways. The first way is, I would say, more traditional, the way that DocuSign does it, which is that you have a key in custodial form that is kept, and you use that to sign. But you don't really have full control over your key, or legally you have control over the key, but the key stays with that intermediary. Well, we are pushing this further, and I will explain probably a bit more about this on the Thursday session when it comes to be joined with the identity product, because as Mike was mentioning, all those modules are meant to be working together. So if I were to use the identity module to actually leverage attestation about me to sign, then suddenly the keys are also with me. The proof that I am Thomas is with me, but still I'm using that to sign the document. So there is no need for an intermediary. All the information is available either through the document or through your instance of sign. So this is, for example, the challenge that we are solving here is like if a fraudster was creating so many business of registering and signing a paper for all those businesses, you would have difficulty to trace that. Now, if the identity being used across was actually always the same, and the keys were always validated to be the same, then you would have better way to track and to incentivize people to do the right thing. So how does this work? This is probably an escape from my usual speech around sign, but for the audience. So let's say you wanted somebody to sign a document. You would send that person a link, or they will receive a notification, and then they will log into let's say the DocuSign and the like, and they would actually sign the document saying, yes, that's me, and based on the email, based on the IP address, and that would stop there. That's one of the way we can function with an nChain sign as well. And it would give the ability to have those proof on chain, but that's not where the real power is. The real power comes with the next step, where this user carries out identity authentication. When you do it with DocuSign, it's basically through using your email. What if you were to be able to use something called verifiable credential, decentralized identity to actually sign your document? That's where the real power is going to be. Okay, so moving on to the demo. So today for the demo, I'm going to show you the custodial model, just for the sake of staying on track in terms of time. I don't know where we are. Okay, so I better hurry up then. Okay, so very briefly, you will see that at no point in time we talk about blockchain here. This is a product that does document signature. So here in this instance, Jane Doe sent me a request to actually sign the document. So I just have received it. I will just review it and say, okay, this document looks fine. I already filled it up. I don't have to sign, but I have a second document to sign. In this case, okay, well, it contains some information about me participating. I will click here to sign with my visual signature. There's two elements in signing a document. There is the digital signature and the electronic signature. Most people, at least in the paper world, will talk about the squiggle, really, what you see. But this is not what proves most of the time online signature. It's going to be the electronic signature, which you don't really see here because it's happening and there is a proof on chain about it as well. But still, that's what will bring power to this document. So at the end of the process, here, because it's a custodial model, so the key we use are actually stored wherever this instance of sign is stored through the use of an HSM, etc., for storing the private keys. But here you could have the same principle with identity, where I actually use my wallet, my keys, to actually sign the document and also to prove who I am. Carry on. Okay, so the document is signed. Now let's show the, so go back to the dashboard and then show creating a new document. So here, similar to how other products also do it, we just create what is called an envelope in which you are going to put your contracts, your different paper, everything you want people to sign. So we added we added quickly 2 documents. Click on continue, add the recipients. So here, the 2 recipients that we add is one that is an authorizer, the other one is a signer. Depending on your use case, you may have even more. It depends how many people you need it to be signed with. You have signing order if you wanted to have people in parallel or in sequence. What is the impact of doing all of this? While this is happening, you can carry on, Leo. I will just explain a few bits. So what is actually happening on chain for the audience that are curious? So from those documents, except for the visual signature that is added on top, this document will be, a hash will be created of it to make sure that the document is unique and it has not been tampered with. We are going to make requests to the different people that needs to sign to actually sign over this hash. So a transaction will be actually completed only if the right public key, so the people that have been added to sign the document, are actually using their key to sign the document. So that is going to prove that the right person or the intended person has signed, and that proof will be on chain. The other thing that we'll have is obviously a recap or a summary page at the end of the document. Here, what Leo is doing is just adding, all the information that you would expect a person that is visually signing is adding. So the first name, last name, the signature, the date, etc. The beauty of it is the way that it has been implemented here. This is technically modifying the document, right? Because you are adding things over time. But in reality, the way it's implemented is that those do not impact the actual hash of the document, because this comes as a layer on top of the document, so it's not actually impacting. So you have still a way to prove that he was signing on the right original document. Yeah, that's okay. You can continue, just because you didn't do the second document. And then you can send it for signature. And then the process will be the first one you have seen before, where I get a notification, I can sign it. So you see that at almost no point in time, except me explaining further the aspect of blockchain in it, we have talked about blockchain. And that's the belief that we have for enterprise to actually accept products that are using blockchain is not by flashing blockchain in their face. It's to actually show that there is value in adding blockchain into it. And I will stop here because if we have only a few minutes, maybe to open the floor for questions. Oh, okay.
Any questions here? Yes, one question coming right away.
Simple. What does it look like when I open the signed PDF in a classical reader?
Good, very good question. That was one of the assets to implement the signed solution. So you have two types of signatures that are being made. One on the overall document, which is what you see in the Adobe PDF. So this one, when you deploy the signed application, you can actually use a certificate that has been issued to your organization to say, I overall signed that the process was followed correctly, and use that to actually flash green, for example, in the Adobe Reader. And then you have the signature of each individual that is also appended to the document and to the chain.
So I think with a classical approach, I open the document, I can see the fields, each with a timestamp signature. But currently with the nChain solution, that's not there.
No, that's also there. That's both are there. Yeah.
So in Adobe Acrobat Reader, I can see those small pop-ups in there.
Yes,
sign.
it's on the left panel, I believe, or is it at the top? One of the two. But yes, it looks like it shows as valid with all the fields actually completed.
How does Adobe the reader connect to the blockchain? How does it?
It doesn't have to, because actually the information that is in the document and WhatsOnChain is on both on both the documents.
Okay.
The two are just equal.
So only the person who wants to verify, he will then connect the dots?
Yes, that's part of what the verifier would do. And we
Okay,
provide the flow. Actually, as part of the PSP portal, you can also see all the technical documentation on how it's done. It will give you those details that you are looking for.
So I can see the timestamp, but I cannot see the verification within Adobe Reader. Is that correct? Because I think with the classical VeriSign, Adobe does show me the timestamp and does show me, yes, it is valid. Is that the same?
Okay.
Now?
Yeah.
You
So
know?
in this case, what it will show you is that yes, it has been signed by a legitimate entity, but for the verification process, yeah, it would be through the sign portal or the verification tool that we give you additionally, not directly in the document. In the Adobe Reader, if you see what I mean, because you mentioned the two. Document is signed properly, but then verification, the Adobe does not yet connect to the service that we provide for verification.
Exactly. So as a company, I would have to have access to your portal in order to sign. And also as a verifier, I would have access to your portal to verify.
Correct. Yes.
What's the cost
of doing verification or
because
of the product?
I guess you won't charge per signature, but you will have like a monthly subscription.
Yeah, that's one of the models we are investigating. We are going to see, because we just launched, we are going to see as people pick up the solution, what is the best approach. But yeah, probably licensing product rather than transaction is the way that we would go.
Okay, thank you.
But verification is part of the story always, as I said earlier, end to end. So we provide the tool to write, but also to verify.
All right. Thank you very much for the presentation. And we have opportunities afterwards to ask questions as well once the event has wrapped up. Thank you, Thomas.
Thank you.
All right. We have a very exciting presentation next. But before we begin and bring our next presenter up, if when I say Ty, you say Everett, Ty. And when I say project, you say Babbage, project. All right, we have the Wonderkind himself coming up, someone who data sovereignty and ownership, returning the user to the center of the process for networks. This is Ty Everett. Welcome.
All right. Clicker anywhere? Let's see. Thank you. All right, everybody. Talking about some new things today. So, Bitcoin for a long time has been limited in one important way. We have scripts. These scripts are predicates. And when you want to actually go beyond that, there's some challenges. So what I'm going to be doing in this presentation is I'm going to be walking you through some of the technical breakthroughs that I have come across with my team as we have been talking about building a general purpose CPU that uses the Bitcoin UTXO architecture. As part of this, I've developed my own instruction set architecture and assembly language for this new CPU, and it utilizes UTXOs to perform multi-stage computation, including recursion, subroutines, loops, and the ability to compile higher level programming languages such as C, C++, eventually even things like Java, JavaScript, Python, down so that you can express things within Bitcoin, interacting with the capabilities that the blockchain provides. So firstly, I'm going to talk about some of the difficulties with multi-stage computation. And then I'm going to cover kind of how we've been able to overcome those difficulties. I will provide some examples. And then I'll get into the architecture of the CPU itself. We'll walk through how it works. And then at the end, we'll go through some of the implications, use cases, and applications of this new technology. And if there's time, which I'm not sure, I will answer questions. So first up, when we are in Bitcoin, we have scripts on outputs. In Bitcoin, transactions exist. They are the fundamental way that we interact with the blockchain. There are inputs and there are outputs. The outputs have predicates, which are a particular type of a lock, in this case, to kind of secure our coins and make sure that nobody can run off with them without our permission. And they set up all of the rules under which we evaluate the, kind of the potential people who try to unlock our coins and use them. There can be many ways to unlock a particular output. Outputs in Bitcoin represent outputs in Bitcoin are what represent tokens. So things that represent real things of value, right? A token is something that represents something of value, and they're represented with outputs. And so you can set up some basic constraints within these outputs. Things like even enforcing constraints on what the next transaction can be. So that's known as stateful UTXOs or stateful smart contracts that have a state that persists over time. However, it's challenging to have contracts that have open-ended, undefined number of future sequences. I'm not activating this yet, so I'll go to the next thing. But I was still just kind of covering some groundwork here. Essentially, what we're talking about here is these outputs and the constraints that can be applied to them. Right now, if you want to set up an unbounded set of, if you want to allow the person who's solving your smart contract to describe the solution to whatever problem you propose across multiple transactions, multiple spends, there are problems with that, right? Because if, say, Alice creates a smart contract that has an output, and then Bob wants to describe the answer or the solution that unlocks that smart contract across multiple spends, it's a problem. The reason why that's a problem is because, well, Bob could broadcast a malicious partial solution. And what that means is that the UTXO, the output that Alice created for her smart contract, has been corrupted. And so if there's a partial solution, then, well, you can't actually get to the real one if you make some missteps. So let's jump into an example. So suppose we have Alice, who is going to propose a new contract as an output in a transaction, which is how you propose all contracts in Bitcoin. You have some output that describes the constraints under which the puzzle can eventually be unlocked across, one transaction or multiple once it kind of releases itself. And suppose Bob comes along and he's going to offer the solution. So he's going to start describing his multi-stage solution across multiple transactions. So transaction 1, transaction 2, step, 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 right? We go through and we put in the right information across each of the different parts of the transaction, or each of the different parts of the solution, which can be described in this case across multiple transactions. However, what if Bob makes a wrong step? Well, he's broadcasting these transactions out to the network, and now there's a UTXO that Alice created that is now kind of in an untenable state. We can't use it, and so everything is locked up and a little bit broken, and that's not good. That's the fundamental problem with describing multi-stage computation on Bitcoin, and thereby allowing us to eventually achieve general purpose computation on top of Bitcoin, which is something I'll get to. But as of right now, we have this wrong step made by Bob, and the UTXO is locked. Nobody can use it. And so, maybe the answer is that if Bob hasn't actually found the solution, then he shouldn't broadcast the transactions, right? And that would solve the problem. Except what if Bob was evil? What if Bob was just going to try to lock up every UTXO created by every person who is trying to just get solutions to their problems? That's going to be a little bit difficult for everybody, isn't it? nothing's going to work. You're not going to be able to describe things. The entire world is broken. This is Armageddon. We should cancel the London Blockchain Convention because we're all just, no, there is a better way. We have a solution to this. And our solution involves a thing called a solver's bond, a state reset, and a time lock. We can combine them together, and we'll describe how that works in a second. So, when Bob goes to solve Alice's contract, Bob is actually going to put in a little bit of his own money and put up a bond. So he's kind of collateralized into the system. That's the first step. Then a timer starts. So he has a certain amount of time to actually arrive at his solution. And if he does not arrive at the solution within the amount of time specified, then we've actually recorded an original copy of the initial state of the UTXO prior to Bob's involvement. And after that time has expired, we can go back and we can reset the state of the UTXO back to the way it was, and anybody can do this before Bob was involved. Now, those transactions, that record of Bob's failed attempt to broadcast a multi-stage contract solution, is recorded on chain still. But now, number one, Bob loses his bounty. And number two, anybody else has a stronger incentive to come along and attempt their own solution. So what this does is it allows us to reset the state of UTXOs and achieve a world where we can have multi-stage contracts on Bitcoin. So that's the initial part of the solution. So, that's the initial thing. Let's have an example. So, like we had before, someone's going to get started, and Alice is going to propose a contract. Bob is going to post his bond this time. The timer is going to start. And then Bob is going to attempt his solution. Now, either one of two things is going to happen at this point. Bob's solution is going to satisfy all of the multi-stage constraints across many transactions that eventually unlocks the UTXO or achieves some state checkpoint, at which point he is kind of in the clear, or he's not. So is Bob's solution valid? Well, if so, everybody is happy. But if not, then eventually that UTXO is locked. Nobody can do anything with it, right? We saw those padlocks before. Well, eventually that timer is going to expire. And then someone is going to come along and reset the state of the UTXO back to how it was before Bob was involved, only now Bob has lost his money, and Carol, some other individual in this equation, can come along with a higher bounty and attempt the same solution, and this will continue indefinitely until the checkpoint is reached or the ultimate UTXO is consumed and broken down. So in this way, we can achieve multi-stage computation, and that's our example. So there we go. Everything's all good, guys. We don't have to worry. No Armageddon. We can bring back all the things we're doing, and we can actually do some cool things. So this is a cool theoretical idea, but I want to talk for a second about how we can do it, kind of, what are some real world applications here, right? Like what is this useful for? Well, I talked about multi-stage computation within the context of a single solver and a single person who is proposing a contract. It allows unbounded loops, of course, things like that, right? The number of transactions in your ultimate chain does not need to be part of the original UTXO. You don't need to have to know that ahead of time. But you can also do things like real-time data sources from signed oracles. So you can have contracts that, while they're being worked on in real time, incorporate things like oracles that sign things like the weather, and that changes over time. And the rules of the system in which you are operating, the UTXO, the constraints that govern it, can be updated dynamically as solutions are being proposed and as new people are maybe providing different data sources for those solvers for lots of things. Real-time data sources, really useful. Next up, if you don't know how many loop iterations you are going to need in your solution, well, this is the thing for you, because just get to the checkpoint and you don't lose your bounty. Very simple. Custom and dynamic algorithms. So I'm going to talk about in a second how the CPU works and implements this into an actual instruction set architecture and assembly language, and how we can build on top. But basically, if you have done anything with early computers, you'll know about peek and poke, and this idea that you have the ability to write things into memory and then actually, as part of your program, accept user input, code, like type in things into memory, and then jump to that location and dynamically execute custom algorithms as part of the evaluation of whether the solution is valid and subject to other constraints. So a little bit more complicated than it sounds like, but that's fine. Also, if you want to code up a simulated world in which, like a game world, for example, or some simplified model of the real world that could even be extrapolated back onto the real world, things like a simulated postal network where you're trying to simulate all of the packages and all of the trucks on the road and delivering them to people. It's a lot easier when you don't have to code the entire thing in a single UTXO with a single predicate. Just saying. So there is one final class of people who think this is useful, and those are the ones here who think it would be fun to implement a CPU architecture that does general purpose computation and just see what people build with it. So what do you say we jump into the Bitcoin CPU and how it works? Instruction set architecture here. The CPU has 4 registers. It has a stack, and it has a heap. There are various opcodes. It's got a base pointer and an execution pointer and a stack pointer like any CPU. It's coded up in script, and it supports things like JSR, RSR instructions in assembly, so you can do things like recursive subroutine calls. I implemented a Fibonacci counter as a demo. You can check it out on the GitHub, which there's a QR code at the end. Yeah, you've got a lot of different things that are here, but so every transaction is a clock pulse, meaning that you can execute 1 opcode per transaction. Currently, I might add multi-opcode per transaction support in a future version if we can optimize it. But those are the fundamentals. So here it is. This is, if anyone has done things with CPUs, this is on the left, you have the heap, which is where your program code is being executed. On the right, you have a stack. And in the middle, here are representations of each of the 4 registers, the general purpose registers, and then, of course, you have your stack pointer and heap execution pointer. And then, of course, I've omitted a few things like the base pointer and the call stack for simplicity. But let's take it for a spin. So I'll set up the execution pointer, which generally starts at 0, although you can start it wherever you want when you initialize your UTXO. And then we'll set up the stack pointer. And so someone's going to create, on the bottom here, these are going to be transactions that are actually executing the different clock pulses of our CPU. So transaction 0, Alice has written this program on the left in the heap and has defined some rules that have to be done. There's a lot of opcodes for like data input output, all the opcodes you could expect from a rich ISA, such as arithmetic and logic and all that stuff. But anyways, you write your code in assembly or some higher level languages that compiles down to assembly, and then someone comes along and they're going to start to solve it. So transaction 0 is when Bob says, oh, I think I can broadcast the whole chain and kind of get to the checkpoint or get to the terminating opcode, which is called op-win. So we have op-win, which is like, okay, well, we're done. We're going to let you unlock the whole UTXO. And there's some new opcodes we'll get to in a second. But yeah, Bob puts up his bounty, starts the timer, and then starts executing clock cycles. So you can see here, as we do, execution pointer moves forward and various opcodes happen. And then eventually we're going to get to a conditional jump. So jumps on Bitcoin, right? People say you can't do loops on Bitcoin. They say you can't do jumps on Bitcoin. These are all transactions at the bottom, and I've color-coded them. And so we're going to get to our first jump. So ready for this, guys? There's a jump on Bitcoin. There you go. So yeah, you can see that one's yellow, and now we're back up here. So there was some condition that was met, and we jumped back up to the top rather than getting to the green, op win it's called at the bottom, where I've actually terminated the program. So run another loop, right? And there you have it again. We just done another loop in Bitcoin. Now the thing is, when you want to have Bitcoin be Turing complete, as someone told some other people back in 2015, you have multiple transactions, and that's what we're doing here. So we'll go ahead and run another iteration of the loop. And finally, you can see that we've actually gotten past it. And so once you get to the green one, op win has been executed. The program has been terminated. The UTXO is released. The winner gets to have their solver's bond back. So they get their money back, of course, because they found the solution. They successfully got to the checkpoint. And then CPU powers down and they get their money. So execution is successful. That's how the CPU works at a high level. That is with a basic program. A little bit simplified, but you can check out the code, and happy to answer a lot of questions about it if you so inclined. So would you guys like a side of opcodes with that? Firstly, op win, as I described, it's relatively simple. Oh, where am I? Have I lost? Oh yeah, so yeah, here's some opcodes, right? We got op win, which is when you actually want to terminate. So you write op win as part of your assembly code or some high-level language. You could have some like new keyword that we could just add so that it compiles down to op win in assembly. Op lose means you just can't do anything else. It's like halt. And keep in mind, if you halt the CPU, that timer is going to expire. Someone's going to come along and reset the state of the heap and the stack and the pointers and everything back. And then someone's going to start over, and they're going to get to that solution eventually. We got op bill and op pay. So as part of this, we can actually put constraints on the transaction tape. So I say transaction tape, which is the long chain of transactions that we're using to describe our solutions to general purpose computation in this context. And we can require that in op bill, some other input is added alongside the CPU tape input that adds additional money of a particular amount, as defined in register 1, into the value of the contract. So that if you're going to take this path of execution in your code, you can actually add money to the system. And op pay, so because back in the day, Shatters was good enough to advocate we added 750,000 character long, big nums into script and enabled that. You can put an entire output script into a register, and you can put the amount of money you want in that output script, and then into another register. And then op pay forces the transaction that incorporates op pay to actually create that script and actually pay that person for work done, and then continue execution after that. So you can pay out of the system as well. Checkpoint. I talked about state resets, right? And I said you could reset back to the initial state. Well, it turns out you can also reset back to a checkpoint so that people can actually update things. So op win, the way it works, it's very simple. We'll boot up the CPU again, right? Set up our pointers and start executing code. And eventually, you get to, so you can see some transactions happening there at the bottom. And eventually we'll get to op win, and off you go. You win. So multi-transaction chain, however you got there, whatever other opcodes you had to execute, whatever input, you have like op read, which means that you can actually read user input from the transaction tape or from that point, and you can hook whatever I/O devices you want up to it. You can do memory mapped I/O as well, which is kind of cool. You have upload and upstore, things like that. Anyways, that's op win. Op lose. Let's run through this. Let's actually think through how this applies all the way back to the original description of the solution we made to state resets, solvers bonds, and timers. So we're going to execute an op lose. Someone's about to lose because there's a conditional jump, and they're not going to meet the condition, meaning they're going to fall through, and they're going to execute op lose. They couldn't clear the hurdle. So let's just show that. Once again, transactions are being executed at the bottom, and this person's hitting the conditional jump, but the condition's false, so they lose. Well, what's going to happen then? Anybody want to shout it out? What do you think is going to happen? Right, CPU terminates, nobody can do anything, so nothing happens. And that's going to force the time to expire. And someone's going to come along, because after the time expires, anybody can reset state. And now we're back up to the top. You can see the pointer just jumped back up to the top. Whatever was on the heap and the stack and the registers would be reset back to their original values. And right, new solver is going to come into the equation. They're going to pay a new bond. Mind you, now the old solver just lost their money, so better incentive to try again and get it right this time, right? Don't broadcast. Guys, work off chain. Don't broadcast things if you're going to lose. It's not a smart idea. Let's go ahead and execute another one, right? So someone comes along and they say they aren't going to lose this time. So they actually jump past the op lose. They clear the hurdle. In this example, we've got transactions coming in once again at the bottom. You can see the arrows and how it connects. I just jumped over op lose. This was 162 slides, by the way. And at the end, you actually win. So now that person gets all that money. So that's op lose in detail. And the final one I want to run through is really cool. It's actually something I'm really excited about because you can do so much with all of this, but with this in particular is bill and pay. So suppose we're in some arbitrary, unimportant place in a program, and we're about to run, a couple of opcodes and just, see on the bottom, we're just executing transactions, going about our merry day, and eventually we get to op bill. Well, these are transactions and they spend each other. These are UTXOs. And so as part of op bill, I'm going to require that some additional input is funding that transaction, adding value to the new UTXO, and introducing more funds into the system from somebody who's paying for some service or something, right? Whoever's solving this problem must have decided that this was the most efficient solution, and that as part of that, some money should be introduced so that it can be later paid to some service provider for some action being performed. So just execute some more opcodes. You could jump around, make a few recursive calls if you want, compute some Fibonacci numbers if it's what you want to do. And then eventually you get another thing called op pay. So this one, it's just the opposite. We require some output be sent. And as part of that transaction, you can actually push onto one of the registers the script that you want in your output. And then you can keep going. So pay some person for some service. And then we just keep going about our merry way and just, execute more transactions. So that's how that works. It's really cool, guys. I'm so excited to see what everyone's going to build with this, because now we can do general purpose computation on top of Bitcoin, which we've needed to have for so long. And that, it's, implications and future stuff. Okay. Testing my memory here from these slides. Okay, I can remember a little bit. Okay, unlimited, right. So this is a really cool computer for a few reasons. Because these things, this heap and this stack are stored off-chain, but the Merkle root of the hashed set that is the heap and the stack are stored on-chain, it means that you can have an unlimited amount of memory in your computer, as long as you can give it to the person, and you can also selectively disclose particular regions of memory privately to only solvers who have a need to know. And everything else is off-chain. So we're using hashed sets and doing it that way. As I alluded to earlier, with pushing an entire output script into a CPU register, memory elements are dynamically sized. So put a whole string in there, put 52 factorial in there. I don't know why I like reading factorials, but it was really cool when I saw it run the first time. I was like, oh gosh, I know that's actually 52 factorial. So I was like, yes, this is correct. Anyways, yeah, we have the ability to dynamically size memory elements, and anyone can set up whatever memory mapped I/O they want. So that way someone can, yes, it can run Doom, right? Yeah, we've got a new assembly language. I'll show you an example program here in just a second. Made a new instruction set architecture that has those new opcodes. That's why I had to make a new one. when is the last time we've actually really super duper needed a new CPU instruction set architecture with new opcodes? Because now we have the ability to pay people and stuff. So that's cool. Anyways, yeah, you're gonna be able to compile other things to it as well. This is an assembly language program using the new assembly language, it's pretty cool. If you don't happen to know assembly language, here's a small detail about this program. You can ignore that if you want. You don't have to pay attention to it. Like I said, just yeah, don't 4 million Bitcoins if you say Bitcoin's not Turing complete. This is a really cool computer. It might be the coolest computer ever. I don't know. We'll see what we can do with it. I think everybody in this room could build some fun things. We should like have a hackathon or something. I don't know. Okay, so let me figure out where I am here. Right, we've got so use cases. Adaptive routing in logistics. You can create a simulated world in a higher level language that compiles down to this and makes this transaction tape. And you can simulate postal networks. You can simulate every type of network and solve, any type of problem with those, and incorporate, like I said, real-time data. So you can broadcast part of the solution, hit a checkpoint, wait for the oracle, broadcast the next part, hit a checkpoint, wait for the oracle. The program can check digital signatures. I added like op check datasig kind of thing using the Xiaowei, the implementation that was in script of ECDSA within script to actually verify a signature. But it made the CPU like 8 megabytes per transaction. So that's pretty big, but like right now it's 2 megabytes per transaction. So it added like a whole bunch. So I removed it temporarily, but we can add that back if people want to have like signed oracles and things. We're gonna have to optimize the heck out of this, guys, but yeah, you can do things like in the financial industry, you could incorporate signals from the market and different data sources so that you can do things like dynamic portfolio rebalancing, and you can manage digital assets using, obviously, you have access to the whole transaction pre-image. You can check how particular tokens are being managed and create complex constraints that govern things like tokenized CBDCs and things like that. Combining with our Babbage identity solution, you can do a lot with certificates and linked identity, type 42 stuff. Recommend checking that out. But in a general purpose way, you can be dynamic about what you want to do. Let's see. Yeah, you got some other thing. Real-time data sources, right? I mentioned that. Okay, what's next? So we think this is really cool, the breakthrough with respect to state reset and whatnot. And there's some fun things that we can do on top of it. I think this is more than just a CPU, because in the world, there are things called ASICs, or application-specific integrated circuits, and they're more efficient sometimes in terms of script size. I did write one that uses the same approach, and share more about that in 2025. Yeah, it's more than just a CPU, and there's a lot of different things that people can do. Yeah, we want to see compilers for other languages on top of this, and we want to see people use it for a lot of things. And we also want to make the scripts a little smaller. I heard from, I actually spoke with Craig Wright just a couple days ago, and he says, well, you can use hash chains and make it even more efficient, because of course he would say that. So anyways, in closing, we said 1 million transactions a second would be really cool, but that's only a 1 megahertz CPU, guys. We need to do more. We need to scale beyond 1 million transactions per second, and orders and orders of magnitude beyond. And we're going to. Yes, you can optimize some of this, and it's going to require less transactions than one per opcode if you want to optimize. However, there is a case for generalization, and there's a reason why we don't all have a whole bunch of ASICs running our computers, except for those little things called GPUs. But those came a little bit later. So yeah, we are going to need to scale this network. It is the only network capable of it. And now we can do general purpose computation with UTXOs. Bitcoin is Turing complete. Thank you. Happy to answer any questions.
We'll do some questions in the networking side.
Sure.
All right, we are right at time. But you are welcome to connect with Ty and learn more about Project Babbage during our networking session, which will follow our presentations. We will have a brief bathroom break right now, and then we'll see you all back here in 5 minutes for Mattia from WhatsOnChain. Thank you all. Will be served in the following break session, not this current one.
The landscape of blockchain development is complex, particularly with the core BSV libraries, where scattered forks and alternatives have created a jumble of options to pick from. To tackle this, we've unified them into a new library, ensuring developers have an official SDK which is easy to use, backwards compatible, stable, and performant. In software development, stagnation means falling behind. The BSV library had started to deteriorate with dependency rot and outdated functionality due to the shutdown of the wallet company which maintained it. By thoroughly revising the codebase, we've streamlined it to be more clean, functional, and formidable, now supporting an SPV approach to transaction construction and propagation. External dependencies can slow down maintenance and complicate updates. The SDK was built from the ground up with no dependencies, making it lighter, faster, and a comprehensive educational opportunity for developers who want to go deep on the details. This effort was made in order to ensure a stable, well-maintained core library for applications built on BSV now and into the future. Our ambitions extend beyond the JavaScript ecosystem. We are applying the same principles to develop officially maintained libraries for Python and Go. These tools are not just additions, they're part of a cohesive strategy to provide developers with robust, maintained, and standardized resources that meet the demands of scalable blockchain application development. The BSV Library project is more than an update. It's a strategic overhaul to prepare for future challenges by providing a stable foundation for innovation. We're doing the groundwork so developers can focus on creating revolutionary applications. Join us as we pioneer a more efficient, secure, and innovative ecosystem. The BSV Library Project, building the foundation for tomorrow's blockchain applications.
Hello, everybody. Welcome to a very exciting Code Along session. I am joined with Ty Everett from Project Babbage, and we are going to be covering the TypeScript library, the newly launched TypeScript library supported by the BSV Association that Ty was instrumental in working on. We are joined with some developers. We have Degan, we have Damien O from 4chain, and Jake Jones as well. Both Degan and Jake Jones from the BSV Association, and myself as your host, Manifestable Brett Banfi. Ty, walk us through what we're going to be covering today and how this is useful information for developers to get some experience with building on BSV.
Sure. Thanks, Brett. That was a good little introduction. Happy to have everybody here, firstly. This is going to be a really good opportunity for everybody to really get some more information about this new TypeScript SDK. It's built from the ground up on top of essentially just TypeScript, right? Actually, there's 0 dependencies And it's the best tooling that we have now for building on top of the BSV blockchain. What I'll do first at the beginning here is just provide an overview of the different little sections we're going to be
All
covering
right.
throughout
Next
the course
up,
of
we have
this
Mattia
session.
from
And then at that
WhatsOnChain.
point, we'll...
Mattia, welcome to the stage.
Do we have the little remote somewhere? Oh. Thank you. Thank you. Oh, nice. Hi, everyone. I'm Mattia, product manager at WhatsOnChain at TAAL. Just wanted to give you a brief overview of WhatsOnChain today and kind of the main features, and of course, take any questions at the end. I assume most of you know about WhatsOnChain, but just in case, yeah, it's all in the name. Walk tells you what is on chain, what's happening right now on the BSV blockchain. There's a little screenshot of the homepage. Initially, I was thinking about doing the demo, but figured out this would be easier. WhatsOnChain.com is where you can find our block explorer and explore on your own everything that you're going to see here today. Yes, so this is kind of the main point of WhatsOnChain. We're trying to basically provide you an independent way of verifying that your transactions are on the chain. I think Kurt mentioned earlier in his presentation that since they're mining transactions, they might as well index them. What we're trying to do is actually go away from that way of thinking, and we're completely independent of any miners. We run a full node ourselves, and we're the node that's still very well connected to multiple peers, but we have independent infrastructure, and what you see on our website or through our API, you can be confident that's what's happening on the blockchain itself. Like I said, I wanted to run through a few of the major features that we have on the website and, of course, in the API. So let's go and do that. So the first one to showcase is our stats dashboard. This is essentially a high-level view of what's happening currently on the chain and in the last 24 hours. We include some of the main metrics there, and we try to update it live or as fast as possible that we can. And of course, from there, you can dive deep to any of the metrics that you see there. Some of the examples are the total transactions in the last 24 hours, or some miner statistics, and our top tags. And tags were mentioned by Kurt as well. So this is one of the ways you can filter transactions on the BSV blockchain. And there's a set of features that Walk offers for that specifically, where we're helping you track different trends, different protocols and apps that come into the ecosystem. And you can see across different categories, you can see how they behave over time, and a few other interesting metrics that come with that, like output volumes, the number of specific outputs or transactions that we found, the size of the data that is associated to them. So essentially, if you're interested on what's exactly happening on the chain in terms of applications and protocols, you can look at it here, and you can filter, dive deeper into different either categories or specific tags. You can look at different time periods and so on. The next one is our plugins platform. This one has been more and more popular recently, but what it does, it helps our builders, our users, expand their experience on WhatsOnChain. So we're building the Explorer, we're doing the best we can, we're listening to your feedback, but we're also allowing developers to build on WhatsOnChain by using plugins. And these plugins are usually either on a single output level or on a transaction level, meaning that you can have either, and does this work as a pointer? I'll try. Nope. Okay. So at the top, you'll see one of the newest plugins that was developed by WhatsOnWallet.ai. And it's presented as a tab on the transaction page, and it allows you to visually browse a chain of inputs and outputs through transactions as kind of a graph. It's interactive, and it was completely built by that team, WhatsOnWallet, and what the platform allows is very quickly be able to deploy on WhatsOnChain. You can also keep a plugin private. You don't have to publish it publicly. So if you build something for yourself and you want just yourself to see it, you can keep it in your private repository. Here's at the bottom is a fun example of the 3D model viewer. This is an output level plugin that essentially decodes what's the data that's contained in the transaction output. So you can essentially any type of data that is contained in the transaction can be decoded and presented through our viewer here. There are multiple already decoders available, and more to come if you decide to build. For the platform information or for any information, just go to WhatsOnChain.com, start browsing. There's a really good visual guide for plugins, especially how to build. We have examples of different plugin types that you can build just to give you starting ideas. And all you need to do is essentially publish a PR at our GitHub repo, and we'll review it, and it's going to appear on WhatsOnChain. I wanted to address this one thing that we've been working on recently, and that is kind of trying to replace Electrum X. And Electrum X, just for anyone that's not familiar with it, is essentially a way of tracking UTXOs. It's a solution for tracking UTXOs. And what we found is that with the scaling of the BSV blockchain, there's been some limitations of that system. Plus, also, it has not been maintained for a while. So we decided to build an in-house solution for it, the UTXO store. And essentially, we're working on it to continue scaling with the BSV blockchain. And it enables tracking of addresses, script hashes, spent outputs, etc., easily through our API. And it's already actually used by a couple of big wallets and other apps to power their systems. So you can see more details in our API documentation for not just these features, but the entire API that allows you to build using WhatsOnChain. So any transaction information, any block information, in case you want to stream from the mempool, we provide a lot of features that enable easier building on the BSV blockchain. And a lot of the stuff that we've built, including this, has come from interacting with our users and getting feedback, getting requests, and building following those. Wanted to briefly touch on the API pricing. So the WhatsOnChain API is fully open to start with. So if you're exploring building on the BSV blockchain and you're okay with up to 3 requests per second rate limit, you don't need an API key. You can just go to WhatsOnChain.com, look at our docs, and start playing with the API. But if you need more, if your company is growing, if you're getting more users, and you need more from WhatsOnChain, there are several packages that we offer depending on your needs, with different levels of support, with different rate limits. And we, of course, have also an option for anyone that has any special requirements that are not satisfied by the existing packages. Come talk to us either through Telegram or through the contact form on the page, or reach out directly to me. We can discuss. We can enable custom endpoints if you need them. Potentially even dedicated infrastructure if that's required. Essentially, grabbing an API key is super simple. You register on the TAAL platform, platform.taal.com, and you can quickly subscribe through Stripe and get your API key and get going. I mentioned our community. So this is the main way we drive development of WhatsOnChain. Our Telegram channel is super active. We have about almost 500 members now, and we get a lot of feedback and questions and suggestions and requests there. Our developers monitor that channel as well. You'll see me there as well. So we highly suggest, if you want to interact with us, that's probably the best way to go. We also have a Twitter account where we provide all of our product shipping and announcements, so you can follow any new releases that we have. And yeah, in general, Twitter is a good place for monitoring what's going on with WhatsOnChain. I mentioned building plugins. Like I said, super easy. We have a guide on the website. Here's a little preview of it that kind of guides you through thinking about your plugins. Yes. See. Yes. So this is pretty much what I had for today. Wanted to leave time for questions. I wanted to make it quick because I assume most of the people are familiar with WhatsOnChain. So if any questions, let me know.
Question from Degan. Here you go.
Not strictly a question. I just wanted to say thank you for implementing my change request, which was to have headers by height. We've now integrated it into the TypeScript SDK as default provider.
Amazing, thank you, and keep the feedback coming. This is why we have these channels, and it helps us direct our development. Thanks.
Appreciate it.
All right, and we have one more question over here, and then we will be sharing a presentation from Gate to Chain.
Just to find out if you've done any testing alongside the Teranode projects, because obviously that's going to scale massively, and you guys are going to have to scale alongside it to keep up with demand.
Yes, so we're keeping a close eye and ear to the ground for Teranode. We're talking to BSVA. We just talked to them actually last week. So we're going to make sure that as the development progresses, as the testing on their side progresses, we also plug into that, and we make sure that we can continue supporting the BSV blockchain in the Teranode world as well. There's a lot of still unanswered questions there, but we have a close relationship with the team at BSVA, and yes, the testing is going to be happening, and we're not gonna discontinue any of the current support of the SV node as long as there's users that have the need for it. But we are also going to make sure that we support Teranode as it happens. So we're going to be there for that for sure, for the scale. We're essentially, most of the stuff that we're doing is to help to scale with the BSV blockchain, be it in the SV node world or the Teranode world. Thank you.
Right. All right. Next up, we have a presentation from Gate to Chain, and that will be followed by a short coffee, tea, and juice break. Thank you.
Okay, my name is Tony Quesada. It's like, okay, it's Tony Quesada, and I am the CTO of Get2Chain. So before starting the presentation, this presentation is focused on show two products that we have. But before starting, let me talk about what is our main focus of Get2Chain. Well, our focus is helping companies to turn data in evidence. What's the problem here with the data? Okay, everyone is saying, people is saying, oh, data is a new oil, it's the future. You have to take care. We're going to give you a new. Okay, it's better. Right? Okay, better. Oh, much better, right? Okay, what's happening with the data? Well, in the artificial intelligence, with the rise of artificial intelligence, the people, the users, cannot know if they cannot trust in data because artificial intelligence can replicate or manage that data. So we have to focus on integrity. That's the solution. So for us, the solution is having time stamping, digital signatures, and also access controls. So that's the thing that we provide to our customers. So we are focused on create tools for allowing our clients to get an easy access to blockchain technology because it's a solution for the data, as I told you. So that's the thing that we do in Get2Chain, helping companies turning data into evidence, facilitate the integration with these integrity layers with existing systems because it's very hard to integrate with blockchain if you don't know the technology. So we like to help companies that they don't know anything about blockchain, and we allows them to connect with the blockchain and start using time stamping. That's the point that is removing the friction. This, as I told you, it's very hard to connect to the blockchain if you don't know about the technology and all the things that you have to control. And for that, for these companies or clients, we are reducing the cost of development because they don't have to investigate and spend time knowing about how develop or interact with the blockchain. So in Get2Chain, we have two solutions, right? One is a SDK for data integrity and tokenization. This is that we called Get2Chain Suite. And I'm going to explain how it works. This solution is already live. So we have some paying clients using our SDK. And we will show you how a user finds in our solution and how the user interacts with Get2Chain. So what we are providing with this Get2Chain suite, we are providing a wallet infrastructure. We have provided payment channels, direct payments, conditional payments, data integrity and storage, and digital asset and tokenization. Well, for us, we create an abstraction layer that interacts with the blockchain, but we are focusing to seems like a software as a service. So usually the companies use a lot of services as a software as a service. So we like to give them the same experience in order to be familiar with. When you log in and register in the Get2Chain, that's the first thing that you get when you register it, and it's a dashboard. What this dashboard is a summary of all the things that you have in the suite, right? We create every client can create more than one application, but application it's an abstraction of what is a metanet tree for each application. It's and also for a wallet, admin wallet. So we decided to create this this abstraction of the blockchain and call it application because a lot of users use application better than use a wallet. Or it's harder to understand. So in these applications, you can create users. It's another abstraction that we create. Users are like wallets. So you can manage, the admin can manage the users of the application, and each user has its own wallet. So this is a dashboard. Only the admin can access that dashboard. You can also, as another SaaS services, create your team, as you can see in the following presentation. But here is a summary that you have. You have transactions, on-chain data. We also support for overlay storage. We are not putting all the data in blockchain. So we don't know if the miners is going to delete the data at some point or not. So you can choose whatever you want, because Computation Suite is a library that you can install in your backend or your frontend. We can both solutions. You can use whatever you want, or the solution that fits better for you. And you can choose whatever you want to write data on chain directly or on external storage. Also, we have support for encryption your data. So you can write data on the blockchain, but it's not public. But also you can write a public data if you want. So this is that you can see the application. So what's inside each application, what you can do. Okay, here you can see the events that the admin are doing in this application. You can count the transaction that you have. You can see the users. It's in this way. The user that this application have. These users, as I told you, it's a real. It's an abstraction of a wallet. So, but we call users. And also, I forget to comment that we are linking also each application to a domain. This is the reason is because we are creating a pay mail in order to receive payments to that application or this application user. So each user can receive via pay mail money from outside. So, and the way that we use the Computation Suite is via our implementation of our library. So we are providing a token. This is a sample token. It's not working, but we're providing a token that you can use within our library. So with this token, you are authenticating as an admin in this case, and with this token, you can integrate get to your library and start creating another users, and each user has its own token for that. So as I told you, all the Computation Suite can add people in your team, share one application, the application that you want. You can invite people to manage as admin always, because all the users that are creating inside the application has his own credential. This is only for the admin of the applications, right? So here you can invite and add people to the team. And the way that we manage this is, for us, it's very important to remove the frictions of you can find in the blockchain. So you here don't have to think about BSV or whatever coin that it's underlying the technology. For here, we are focused only in the use. So we are providing this technology for the end users, and they pay only for the use that he wants to spend each month. For example, in this plan that I have here, you have 1 million of transactions. So if you do more, you have two options: or pay more, or pay as you go. So you have some a kind of storage that you can use, and also you can issue a number of tokens. Exactly. So as you see here, this is focused as a SaaS service. You don't need to know these hard things about the underlying technology that is blockchain. You only want to get the benefits of that. So that's the idea. We are focused on create an easy platform for the for our clients. So as example, because it's very hard to put all the documentation here, but if you register, you can find the documentation of our platform. This is an example of, can you create an application user, right? So our technology is based on JavaScript. So you can use this in the browser, and also you have another library that you use in Node.js. With that, you can create an application user, and it means you are creating a wallet, but for the end users, it's like a user, not a wallet. But in the underlying technology, it's a wallet, really. So here is an example that you can easily create an application user. And also I have another example here that it's creating objects. Well, as I told you, when you create an application, you are creating a metanet tree for that application. And only the admin can have access to that some parts, but user can has his own data because it's encrypted with his own key. So here is an example of how you can get a user object. So we're creating objects, we're using metanet trees, and is a way that we manage, but for the end users, it's like they are using or putting objects and they don't know that they are really creating a metanet object or using the blockchain. So that's the way that we create this layer. So making the easy ways possible to the end users to have that solution. So with this technology, this is our low-level technology. It's very flexible. You can do a lot of things. We can create tokens. You can conditional payments. We have a lot payment channels. You can, for example, create like a video and pay as you go, or for the timing that the video is playing. And you can do whatever you want, but continues being hard for some kind of user. So for that, we decide to create another solution that is built in top of the Get2Chain suite. That is Trace. What is Trace? Trace is the easy way to create events timestamping on the blockchain without need of knowing any kind of thing about wallet, users, blockchain, and transactions. So what's that? What is Trace is a platform that allows you to create a digital twin or digital object that it's safe in blockchain, right? So with what things we can do with that? Its entity, digital objects. I will show you another example that are built on top of Trace after that. But what is digital objects? Digital object is some kind of object that can have some events. So I will show you an example how it's working. But here in this dashboard, you have all the stats. This basic information as a service that we have here. And here you can create a lot of things. For example, in this example that I show you here, it's like a watch store. Then we have each specific watch, and we have his digital twin mapped on the blockchain, right? So here are a lot of watches that I have, and I can control what happens with each watch in its time. For example, here, well, also we provide in Trace a way to organize you that is creating category and subcategory for each digital twin. So it's a way that you can manage your digital twins. I cannot show you here, but here also we have smartwatches and also we have another kind of categories. But it's a way that you can manage all your data. For example, we have another solution that is for creating certificates for universities, for example. And the way that you can manage it is for each course. For example, you can create a category or subcategory for each topic, each course, if anything that you can think about. It's a way to organize your digital assets. So in this case, I'm creating these digital asset classic watches, and this is created on chain. So you can anytime go to WhatsOnChain and see what's the meaning of this digital asset, but also you can create events for each digital asset and track what is happening with this specifically digital asset. That's the idea. For example, in this case, at some point, this watch is sent to the store. Pues we can create that digital store and we can add some metadata or files attached to each event that also is recorded on blockchain. So what's happening with that? We have a lot of events and we are trying to create the easy way to a company can integrate his data to the blockchain. And we have a very flexible platform also in Trace, because here I am showing you some events, but these events are generic. So you can create your own events. In Trace, we have an API that it's impossible to show you here, but you have an API that you can create your specific events. We have, let me show you before here, but because I didn't comment that, but we have different type of events. We provide like a specific ones, like default ones for telling in some manner that these are updates, transfer, stolen, if some digital twin is stolen, for example. But you also create your custom events and add specific metadata to each object or event. So with that solution, we're covering a lot of stuff that client wants to do, because if our default model that we use in Trace doesn't fit with your solution, you can add some metadata to each element or object or event. Here, as you can see, you can add any kind of information to the object. You can add images and all these attachments that is for event or for digital twin are also linked and stored in blockchain. It depends, but are linked in blockchain. So with that, you can control the integrity of all the data that it happened at some time, at some point. The way that we interact with that, because this is a Trace dashboard that it's just like a viewer, because our idea is that this solution can be integrated with a lot of stuff, for example, a CRM, in order to automatically each product that you add in your CRM get linked automatically in the blockchain. So that's the idea. So for that, we provide an API that allows you everyone to integrate, and you can add some kind of permissions. It depends, for example, if you have an application that have a CRM and it's writing these events on blockchain, for example, a manufacturer or a factory or whatever, can create an event, but could be the client have another application and only wants that they can read or get access to the digital twins. You can also create another connection API point in order to get that information. So that's the idea of permissions. How Trace, as you see, is very flexible because you can add metadata in each event, you can add information in each event. And for that, we create we built on top of Trace, because Trace is built on top of Get2Chain Suite. And here we get on top of Trace some modules that is working using the Trace API, right? And this is an example. We have 3 suppliers is not live now, but we are working on that now. We have the digital product passport that is like a tool in order to, if you are not going to integrate directly with your CRM or whatever you use, you can use digital product passport in order to manage your twins or your digital objects in an easy way. That is that platform that you saw here. This is the same account connected, so you can see here what the digital twin is, if you want to create an update, or if you want to create a new digital twin. So, and the other modules that we have here is, for example, Diploma. Diploma is a module that's, as I told you, for create a certification for courses, universities. And how it works, it's built on top of Trace, and you can choose using the category and subcategory feature that trace have to create diplomas for each people involved in that course. For example, this is an example, right? And with that, you can manage all this stuff. So here, for example, we are using some metadata stuff that we also provide with Trace API for adding more information that the default stuff of Trace is not providing. So now we are looking collaborator developers in order to increase the use of Trace and Get2Chain Suite. So how is the way that you can collaborate with us? The first of all is trying or use the Get2Chain Suite. And if you have some solution that fits well in our solution, we can integrate it within Get2Chain Suite, because we want to deliver this solution with a lot of flexibility to our customers. We can create a trace, another trace. You can use as a developer Trace for using data integrity, because it's very easy to integrate. You don't have to think about wallets and all the blockchain stuff. Is basically transparent. So you use your regular backend authentication method and use Trace and put data, and the data is stored in blockchain automatically. So, and also, as you can see, we are creating modules. We are now going to launch the Trace store, that is going to be a marketplace. And also we are providing a SDK in order to develop these products built on top of Trace. With that product, we are going to create a marketplace within Trace for the users to be able to share development. So it has no sense to have the same solutions implemented over and over again. So our idea is to get a lot of people involved in BSV, because we believe that the future, as I told you, is blockchain. We believe that it's very important to have this data integrity in the future, because every day we have a lot more and more data. So we believe that this is the future. So we want to everyone can access to the blockchain, and this is our focus, to be the blockchain as easy as can be. Create this data integrity and allows everyone can use that. So this is the end. So I think you like it, our solutions. I've been working so hard with that. So thank you.
All right. And now we have a brief break for juice, for coffee and tea. We'll be back in 15 minutes.
The landscape of blockchain development is complex, particularly with the core BSV libraries, where scattered forks and alternatives have created a jumble of options to pick from. To tackle this, we've unified them into a new library, ensuring developers have an official SDK which is easy to use, backwards compatible, stable, and performant. In software development, stagnation means falling behind. The BSV library had started to deteriorate with dependency rot and outdated functionality due to the shutdown of the wallet company which maintained it. By thoroughly revising the codebase, we've streamlined it to be more clean, functional, and formidable, now supporting an SPV approach to transaction construction and propagation. External dependencies can slow down maintenance and complicate updates. The SDK was built from the ground up with no dependencies, making it lighter, faster, and a comprehensive educational opportunity for developers who want to go deep on the details. This effort was made in order to ensure a stable, well-maintained core library for applications built on BSV now and into the future. Our ambitions extend beyond the JavaScript ecosystem. We are applying the same principles to develop officially maintained libraries for Python and Go. These tools are not just additions, they're part of a cohesive strategy to provide developers with robust, maintained, and standardized resources that meet the demands of scalable blockchain application development. The BSV Library project is more than an update. It's a strategic overhaul to prepare for future challenges by providing a stable foundation for innovation. We're doing the groundwork so developers can focus on creating revolutionary applications. Join us as we pioneer a more efficient, secure, and innovative ecosystem. The BSV Library Project, building the foundation for tomorrow's blockchain applications.
Something that's an object, yeah.
Right.
Okay, got it. Okay, so I have something that you press one button and it will generate a transaction. You press another button and it attempts to broadcast it.
Okay.
So I don't know if it'll work. And it gives no feedback. So I should probably add feedback of some sort. I need some help on the, what does the broadcast interface return? A broadcast response or failure, okay.
It returns broadcast response or broadcast failure. The yeah, it'd probably be best to use that. I'm just thinking we would need to use an actual API key for Arc, would we not? Or is it required to?
You can, if you hit https://arc.tal.com, I think it does not check for API keys at this stage. They've got a special deployment that's they're sort of, yeah, they wanted to test the throughput, so they removed the tappy stuff that checks for the API key.
Okay, so I can then actually just make use of this entire, okay, because I was operating under the assumption that I would want to actually, right, but I'll just.
You should be able to just, yeah, I don't know if this is right, but what I've written so far is transaction.broadcast and then new arc with just the URL, because it doesn't have a token. That would be it doesn't have an API key. So I think that should do it.
I don't know if that's an optional, let's see.
Yeah, let's find out. So broadcast response. Oh, this is awesome. You can just click through and it'll take you to, okay, so broadcast response is an object that has status, TXID, and message.
Yep.
So let's say if the status is success, the string success, then everything's fine. So I'll check that. And so res status equals success. Or if it doesn't say success, broadcast failed.
All right, I think I'm about in the same state as you, Dagan. I should be able to now click the button and see what will happen. So I'll just do that, and here we go. Oh, of course, I have to import Arc. We'll try it one more time.
Dear, I have a problem now. I think that might have worked, and then my app crashed, so I don't know what the TXID was. Oh. Yeah.
I'm looking at the network tab of the browser. I see that raw TX in the payload. I saw Core's cross-origin issue. I don't know if they have access control allow origin for browser-based TX. It may be easier if we want to just dump out the hex and then go to WhatsOnChain and just use that as a. Although it'd be cool to demonstrate in this tutorial as well the broadcast features of the library.
Yes.
We did actually create a broadcaster client for WhatsOnChain, I think, as part of one of the tutorials. So we could, although I don't know if that's actually part of the library currently.
Oh, that's a good point. Yeah, I don't know if WOC has been added. I think I know what you mean.
We could simply just grab the hex and drop it into, this screen here, right? I'm not sure if the ARC side, I'm seeing cross-origin errors. Let me look at the headers.
We can set up the webpack to make a proxy to the from the local host to the TAAL's API. So
it's true. So that would be Webpack. Yeah, that would, because what is this? How do you?
It is proxy in the dev server, I think.
Proxy, and then what? So slash broadcast. See, know what the URL is. Let me grab it here. And that proxy would ignore.
Hold on. Just remove arc from the end, and add arc in place of API. So arc.tal.com, no slash.
Arc.tal.com, and that's it.
That's it.
And then
right now you should. But that I'm glad that came up, because Damien, I didn't know you could set proxies like that. That's cool.
Yeah.
You're missing a comma after the proxy object, but oh well, I guess it's not needed now.
Yeah.
Hopefully it's not needed.
We'll give this a try. It's a much cleaner URL too. So if that's in case, or if that's in fact going to work, then I see a TXID. I think we did it.
Nice.
Cool.
Right. So yep, that's essentially how that works. What I can do at this point, and let me know what you think is best. You think it's best, Brett. We can either move on to questions about this particular thing. I can go through and give a little bit more commentary about what this code is doing, and then we can do questions, or we can just move on to the next piece. Of course, balancing things like time, what we want to get through, and kind of what people want to do.
Yeah, I think let's open it up to any questions or comments about what we just walked through, and hear feedback.
And so we got this code here, and essentially, what we did in this little example is, we made some assumptions. We had a transaction that was where we got our money from. We then had a private key. We had somebody that we wanted to pay, and we used the library's script templating features to just kind of create a simple pay to public key hash payment. Also unlock the previous UTXO, and then add our change output as well as the amount we wanted to pay to the other person. We computed the fee using the default fee computation, and then we signed all of the templates. We then got a response back from the transaction broadcaster and updated that within our little user interface here. That's a brief overview of the code, and happy to answer any questions about it. I think it's fairly straightforward, and there's a written example of this, of course, as well, you can follow along with.
It's very cool. I think the most useful thing is the setting change true, and just being able to, like, if you're just playing around in developing a locking script or something, setting it change true so that you don't have to bother figuring out all of the what the change is reduced by,
right,
and just being able to sort of whatever transaction you create, if you have an output that is the same locking script, then you can literally just update the source raw TX. Like, so I don't know, I wasn't watching the screen closely enough to tell if you're printing the new transaction as hex to the screen. Is that what you were doing?
I did print the TX ID. I didn't print the hex, but I can actually go grab the hex because it's right
in your console somewhere or something.
It's going to be
in the head.
In the oh gosh,
the broadcast.
It's
in the broadcast.
Yeah, it's right. It's right here, actually. Right. Perfect. There it is. So that's the hex.
So you can just copy paste that into your as your new source transaction, and now you have a new source transaction which you can just spend again and create a new one.
Yeah, yeah, that makes sense. So there's that, and then of course, now that I have this this TX ID, what I can do is copy it, and actually we can check to see that it computed the fee properly, right? If I go to just like WhatsOnChain or something like that, I can give this TX ID. And I can see that we had our input, which was the amount that I was previously consuming. And then we had the amount that I wanted to pay to that address. And then, of course, the change. And there was only, I believe, 3 Satoshis as a fee. Is that correct? It looks like. I could be wrong here. Maybe it's
3
Satoshis. Times 10
right.
to
Negative 8 is right. 3 sats.
Yeah, so it computed the fee using the default fee model. So for 3 Satoshis, I was able to do a 1 in, 2 out transaction, and that is essentially the first little goal that we had here in this session, is to kind of demonstrate that. So here we already kind of introduced the concept of what is a script template. And so we're using this pay to public key hash script template for this. And that's what we're using to actually, sign and spend the pay to public key hash UTXOs that we're dealing with, as well as to create the new ones. So a script template is kind of an open-ended way to work with different types of scripts in BSV, and of course, each script template can be configured with different parameters depending on the type of script that you're working with. In the example of pay to public key hash, we configure the unlock portion of the script template with a private key, which is then used to spend or sign the previous UTXO as it's being spent. And then we also have the lock portion, which is how you actually set up where you want your new P2PKH or pay to public key hash UTXO to be going. And For those that aren't aware, dissipated public key hash, it's basically like a Bitcoin address in layman's terms, right? Yep, that's essentially the concept of what is a script template, and that's really moving into the next section here, which is script templates and their utility. Each script template has a lock and an unlock portion to it, and those are used for creating locking and unlocking scripts respectively, for creating and then subsequently spending various UTXOs. We've implemented various different script templates within the TypeScript SDK. I'll go ahead and pull up the interface, which is what must every script template have, and then we can review that and answer any of your questions about the concept of script templates before moving into a more involved example of actually implementing a script template in practice. Let's go to scripts. So I'm just going to pull up the library source code only to show the interface here, which is just so that we can understand what a script template must have in it. So I'm just going to go to script template.ts here. This interface defines the structure for script templates used in Bitcoin transactions, right? It provides methods for creating a locking script, creating an unlocking script, and estimating the length of an unlocking script. So you can see here that it can take any parameters in the lock method, and then it can return either a locking script or a promise for a locking script. And that's basically the first thing that every script template must have. Second thing is, in the unlock one, you can pass any parameters, and then it's going to return an object with two functions, and that's going to be a sign function, which, given the transaction and the current input, will return a promise for an unlocking script. And the estimate length, which, given those same two parameters, the transaction and the input index, will return a number of bytes, which represent the length of the estimated length of the unlocking script in that context.
Ty, can you just give a really quick refresher of what a promise is?
Yes, in JavaScript, essentially a promise is a way to say that you're going to call back to the caller later and finish with a return value. It allows for asynchronous programming because JavaScript is essentially a single-threaded language, but you can kind of defer execution, and for things like dealing with network requests, things like dealing with long-running tasks, you might use a promise to kind of just defer the execution. And the reason why I'm talking about promises in this context is because, suppose I wanted to make an HTTP request out to some API as part of my script template in order to learn what should be the correct locking script given particular parameters. Or perhaps I wanted to do some key derivation operations using something like the Babbage Metadata client or other systems that do asynchronous calling out to different other systems. The purpose of the promise here is just to make sure that those long-running tasks can be kind of set up, and then when they're done, then the promise is essentially a promise for the return value at some future time. The library will know to then expect that future return value to happen once the promise has been resolved, and that way we can be more dynamic about the way that script templates generate both locking and unlocking scripts.
Awesome, thank you.
Right. So does anybody want to wager a guess as to why I had to add the estimate length method for unlocking scripts specifically?
Estimate length because unlocking scripts often have signatures in them, and we don't know how long a signature is going to be to the byte, at least, because it could be, 72 or 73 or something like that.
Right.
Was that the main reason?
Mainly, and then some scripts could be different lengths, and it's useful to know how long we estimate the unlocking script to be sometimes before we sign, and the reason why is for certain fee models and fee estimation. So, you know, we may not know exactly how
Like
many bytes.
a hash puzzle, for example. So it could have a big data blob for all we know that hashes down to something that will unlock, right?
Right, and so by providing that big blob in the unlocking script, you know, the length could be very long, and that could have a big impact on if we're using, for example, fee per kilo, you know, satoshis per kilobyte as our fee model for the transaction. We need to let that fee model have access to that information, potentially even before the you know, the inputs are signed. And the reason why we have to do that before the inputs are signed is, of course, because, well, change outputs amounts will depend on the approximate fee, or the, you know, the fee that we're end up going to pay. And so we should fix those change amounts based on the information that comes from the length of the unlocking script prior to actually signing,
The
right? Because if
landscape
we
of blockchain
signed
development
first
is
and didn't know the
complex,
length yet,
particularly with the
then
core
we may have to
BSV
change the
libraries,
change
where
outputs
scattered
afterwards,
forks
which would
and
of course
alternatives have
break the
created a
signatures if
jumble
we're
of
using,
options to pick
you know,
from.
Sighash single, Sighash
To
all, any of
tackle
that
this,
stuff.
we've unified them into a new library, ensuring developers have an official SDK which is easy to use, backwards compatible, stable, and performant. In software development, stagnation means falling behind. The BSV library had started to deteriorate with dependency rot and outdated functionality due to the shutdown of the wallet company which maintained it. By thoroughly revising the codebase, we've streamlined it to be more clean, functional, and formidable, now supporting an SPV approach to transaction construction and propagation. External dependencies can slow down maintenance and complicate updates. The SDK was built from the ground up with no dependencies, making it lighter, faster, and a comprehensive educational opportunity for developers who want to go deep on the details. This effort was made in order to ensure a stable, well-maintained core library for applications built on BSV now and into the future. Our ambitions extend beyond the JavaScript ecosystem. We are applying the same principles to develop officially maintained libraries for Python and Go. These tools are not just additions, they're part of a cohesive strategy to provide developers with robust, maintained, and standardized resources that meet the demands of scalable blockchain application development. The BSV Library project is more than an update. It's a strategic overhaul to prepare for future challenges by providing a stable foundation for innovation. We're doing the groundwork so developers can focus on creating revolutionary applications. Join us as we pioneer a more efficient, secure, and innovative ecosystem. The BSV Library Project, building the foundation for tomorrow's blockchain applications.
Welcome back, everyone, to BSV DevCon, the afternoon session, and I'm very privileged and pleased to announce and to invite the education team, Kevin Healy and Todd Price. Welcome to the stage.
Thank you. Thank you. Thank you. All right, so we're going to give a quick overview of our courses and the blockchain in general. Just as a developer, what courses may you want to take and how do they fit in? So the first thing you have to decide is, well, what do you want to build on BSV? Because depending on that, you know, there's different solutions. So if you just want to do micropayments, super simple stuff, then you may not even really need to take many of our courses. You can just, you know, plug into an existing wallet or something like that that allows you to do that. And there's all sorts of social networks, Lament and stuff like that that have already done that. We also saw the WhatsOnChain presentation just before me, and they were talking about making it easy to do timestamping and things like that. And so if that's all you're using it for, then maybe you just use somebody else's solution. But if you want to do it yourself, then we have the hash functions course, we have the Merkle tree course, stuff like that that can help you to understand this a little bit better. Another aspect would be the programmable money, right? And to do this, you have to have some knowledge of Bitcoin script. Of course, it could be abstracted with script and stuff like that. And they have their own tutorials, but we just released one, I forget how long ago, but pretty recently, a new Bitcoin script course that teaches you all about this. And then some other good ways of using BSV would be the optimization problems, right? So there's a lot of things that are not, economically like possible in an easy way. Like, for example, the traveling salesman problem. You can't just run that on your computer because once you get above 20 cities, and this is like to find the fastest delivery route in the shortest amount of time. Once you get above a certain amount of cities, there really is no easily solvable solution. So you have to use heuristics, you have to outsource it, or you're just doing guesswork. And there's certain techniques, where people can find a solution that is better than the previous one, but it's not like deterministically like this is the best solution. Somebody might be able to find a better one. And so with these kinds of things, it really becomes an economic problem. And to be able to program this into Bitcoin scripts and then let anybody solve it, that's actually pretty valuable. And it's really valuable, especially when you consider all the delivery routes and a company like Amazon that has, I don't know, millions, billions of packages that they deliver. Think about if you could shave off time. Think about how valuable that'd be, right? And so using Bitcoin script, you can start to solve some of these economic problems. Okay, and then one of the things that Todd has been enlightening me to recently is that, anytime you have a DAG data structure, which is a directed acyclic graph, right? So it only goes in one direction. The arrows don't go back and forth. You can't go to A and then back to, or go to B and then back to A. It's only a directed thing. Well, this data structure is used in a lot of computer science problems, right? So machine learning, versioning systems like Git repositories, project management, right? So let's say you want to remodel this building that needs some work. Well, there's all sorts of different things that go into that. Different stages have to be finished before the next one. And that is outlined like a DAG, right? Project management. And so by having the unique features that BSV gives us, you could weight these different nodes and you could timestamp the different nodes. So like, for example, with the Git versioning system, if you are in one of these and you want to prioritize that something gets done faster, you could just increase the amount of reward or the bounty, and then somebody would finish that faster. And you could imagine how that would work in a project management in the real world with construction and stuff like that. So anyways, that's a quick, overview of some of the stuff you could do with BSV. And with this whole DAG stuff and the overlay, we need a little bit more complex understanding, which Todd is going to give us with an overview of how the blockchain works.
Okay, cool. So yeah, hopefully we're all pretty familiar with transactions by this point, but I want to kind of go through. So, the Bitcoin system seems extremely complex, but really there's only two network events that occur in the system, and they're transactions or the broadcasting, like the proposal of a block. So we've got this transaction structure, and it's a flexible arrangement. We can have multiple inputs, multiple outputs, multiple inputs, single inputs, multiple outputs. But you can see the inputs are flowing from one transaction and being consumed in another, and then that next transaction basically opens up all the tokens that were locked within that input and reallocates them into a new set of outputs. So they're like discrete entities. There's no accounts in this system. They're just flowing from one to the next. And all of those transactions, they start at the beginning, which is the Coinbase transaction. So that's when a miner is, they're proposing the block. They're going to collect the fees and the block subsidy. And so they're doing that from a pool of the coins that have been issued already, but they haven't been distributed onto the network. So they have no input in there because they're just saying, I'm entitled to these coins, and then they lock them with a script. And so these are a bunch of the rewards, which is currently at 3.125 BSV per block. Plus there would be an accumulation of transaction fees on there. So then from the Coinbase transaction, the locked output is unlocked into the next transaction, and then we spend it off onwards. And the structure of that transaction is all passed across the network in clear text. So this is, it looks crazy, but it's not encrypted. It's just simply hexadecimal representation of it. But what it's saying here, you can see the version is the first bytes, and then it goes off along here, the end lock time of the end, some different inputs where you can sort of differentiate where certain value fields are in there. But so what we're saying there is we're unlocking it with a signature in most cases, but it's some value that satisfies the lock puzzle. And then the locking script needs to be, because we're just passing it across in the network, you can't have something like 2 is my solution because everyone else can see it. So the difficulty of that locking puzzle needs to be sufficient that when it's going across the network, it's going to prevent other people from claiming the funds that are locked up within that script. And so with the Bitcoin model, with the privacy model in there, is we have a firewall between the identities because we're using new keys for each transaction. You just have a bunch of outputs that you can solve the locking scripts for, and no one actually knows if you've used fresh keys each time. No one will be able to attribute that to you. So I think that the UTXO is kind of a strange term, so I'm proposing spendable transaction outputs because you have available spendable transaction outputs, and you've got a range of different keys which contain those discrete amount of tokens within each of those outputs. And then collectively, there's a database of all of those outputs that are available to spend by anyone. People say the UTXO set or the STO set, and that's going to be, a giant list of all of the outputs that have been generated by every transaction that have yet to be spent. And so the nodes are all keeping a record of that, and they're going to have to, fetch data from that that STO set when they're verifying that whether or not that transactions or the unlock script that was provided solves the solution for the lock script that it was set against. So these outputs, within the outputs themselves, they've got a discrete sort of data structure. So there's the amount of the tokens that are within there. That's, in decimal there, but normally it's just written in the hexadecimal as well. The length of the script, and then the script itself. And if we then look to what that script is, there's various different, the color coding. So the 76 is actually 118 in decimals. So the 118th opcode is opdupe, and this is basically what is being required from here. So you need to provide a value that when duplicated and then put through the hash 160 op function, then you're going to push this other data onto the stack, and the value that was duplicated and then hashed needs to equal that value provided, so the equal verify, and then you would check the signature that was provided as well. But that's only if this is a pay to public key hash, so the expected unlocking script is a signature and a public key, but it can be anything. It could just be a really large number that was unlikely to be just guessed. So this is just the indication of what it is. And then we have the input structure, which is referencing the previous transaction that generated that output, the index position of which number output it is, the length of the script, the unlocked script itself, and then a value there, which is the end sequence. So in this case, it's in its maximum value of 8 Fs, but it can start at 0, and you can essentially spend that input multiple times in a transaction template until you've got to the maximum number if the end lock time of the overall transaction was set into the future. So it allows for multiple rounds of negotiation or various states of the transaction to be passed from one party to the next. And we sort of, the transaction doesn't just have to be a static thing that's generated right then and there and passed off. Because we have the multiple inputs and multiple outputs, we can actually create transactions in a more dynamic fashion where you might pass it to another party and then they add some inputs into it, or they add outputs, useful in situations of crowdfunding, or it can support any type of conceivable transaction. And so that unlock script, in this case, it's a signature and a public key. So then when we look at what is the signature itself, the signature is having the private key that's associated with the public key, and then using that to mutate the hash of a message. So the message can be any length, it's been hashed and reduced down to a fixed byte length, and then we change that with the private key, and that will be the solution that you can offer to the nodes, who will then say, yep, checks out, and I'll let you unlock those funds. So this is the message, because you hear, oh, you sign a hash of the transaction, but it's not actually the standard data structure of a transaction that you're signing. You're signing a serialized set of values, which are put together in this order, and they kind of bind the transaction. The input, when it's being committed, and when it's being signed, can lock to a particular state of the transaction, but the transaction from that point can still change depending on if you add these values in at certain times. So there's some issues here if we're talking about that we can add multiple inputs or outputs after the fact in certain transactions, is how can we define all of the previous outputs if we're going to still be adding outputs after the fact? How can we define their sequence numbers if they're going to be added after the fact? And if we're still adding outputs, how can we define all those? So we tell the node or tell other people how this transaction is being handled by the use of these SIG hash flags. So all, none, single, we're signing all the inputs, all the outputs, none of the outputs, all of the inputs, or just the one output and all of the inputs, or the ACP is for anyone can pay. So we're signing that input at that point in time, but you can add more inputs after the fact. And so because we've created that message that's being signed in a particular way, depending upon the SIG hash flag used, we have to tell the node to which flag we used. So at the end of your signature, you have a little flag value that you append to it. So the node goes, oh, they've used all. Okay, I'll draw in those data fields or the values from those data fields and create the pre-image in exactly the same fashion, because otherwise you won't be able to create the same hash output, and then your signature verification will fail. So yeah, this is the the sort of the data structure for each of the different flags, and you can see these blank ones. They're not actually blank. They're replaced by a bunch of zeros to just kind of neutralize that field. So there's some interesting things here, and what it's requesting here is it's requesting the lock script lengths of the input, but then in the transaction itself, it specifies the lock script lengths of the outputs. So we've got a bit of a discrepancy here between the required data to reconstruct the pre-image and the data that's provided in the transaction itself. So what's being proposed is the extended format, and that just adds a couple of extra values in the, they use a flag up there, EF, which replaces the first input count byte. And then if you have that flag value, you say, oh, we're expecting to have some extra input fields in this transaction, and they will be the value in the lock script length in and the lock script itself. So that means when the node is recreating the pre-image to verify the signature, it doesn't have to go and fetch and do data retrieval from the STO set. It can be passed those values at that point in time to check if the script evaluates to true or not. So this is kind of a little bit of a flow of how transactions are constructed. So this one, we've got that input's being committed in, it's been unlocked, and we're spending the money out. And we also need to spend, because we've got one BSV that we're committing, but we only want to spend 1/10 of a BSV going outwards. So we need to get ourselves the change. So you create an output that goes back to yourself and is appended onto your, your spendable outputs as a change address. So in the past, they would have, sent the change back to the same address they generated, but then you can start to trace your history through that chain of digital signatures. So you're much better off if you use that fresh key again, so people don't know whether that 0.89 was actually going to to myself or to another party that was part of this transaction. So if we've got, one BSV in, one BSV going out, the transaction is going to be denied because we don't account for anyone, we don't incentivize anyone to process this transaction. So in reality, we've got to give a tiny little payment to the miner who will award the transaction fee to themselves through that Coinbase award. So if we then go back to that lock script, we can see this is the P2PKH, but there's a variety of different scripts that can lock the coins. You can invent any yourself, or you can use these generic sort of templates. So pay to public key hash, pay to a hash puzzle, a multi-sig, which is looking for signatures, multiple signatures combined in there, an R puzzle, so an element of the signature, or they can get rather big and unwieldy. So that's all in in Bitcoin script, but yeah, we've sort of seen S script, and they will create an abstraction here, so you can use more human readable language, like a higher level language, to create these lock scripts. But essentially, if you've created a massive script like that, then your output is a bigger output, and you pay sats per byte or bytes per sat. So you're going to have to pay a bigger fee if you've got a bigger script to that. Additionally, we can embed data into those outputs. And in that case, if it's a whole movie, we might have to pay a larger amount there. And there's two different ways to really add the data. Or there's only one way to add the data, essentially, because you're always having to use a push data opcode to specify the bytes that are going to go on there, because this is a machine that's just reading serialized string of hexadecimals. So it needs to know, okay, the next 100 bytes are all data. So it will use a push data code. But if you embed it onto the blockchain with the op return and then the push data, because of some insecurities in op return back in the day, that those opcodes need to be prefaced with an op false, which then means the transaction will never be able to evaluate to true. So it becomes an unspendable output. So essentially, the op push data, if you don't use the op return method and you kind of specify the data and then instruct the system to extract that data, it becomes spendable. But with the op return, it's not. Excuse me. So the op return is probably more suitable as something like a print line function to embed metadata, timestamps, signatures, proofs, and such like that. Whereas the op push data is more useful for embedding data payloads that you want to be able to perform subsequent operations on, or to process into a next transaction. So yeah, what I want to try to encourage people to start thinking as a transaction is, rather than I generate a transaction and pass it to you, I have a container which I can add inputs to and outputs dynamically. And with the use of the sig hash flags and those end sequence numbers, we can actually make some pretty useful arrangements which people didn't conventionally, I think they haven't thought about using a transaction in such a way, to use one transaction through a product's entire supply chain life cycle. So with the sig hash flags, we've got a lot of flexibility here. So let's look at this first input. It's been signed with a anyone can pay none. So what that means is anyone can add money into this, but I haven't locked it against any output. So if I gave this, to my daughter, she now has one BSV that she can, if she was, not 7 and she was a bit more savvy, she could slice in a lock script and add it into that raw hexadecimal, transaction data, and it would be a valid transaction. So this is like a blank note, a bill that you can go around and give someone. Here's a BSV. If you can figure out how to, add an output in here, it's yours. So that's it's useful in certain arrangements, but we might find that we want to lock it, to if we want to use the sig hash none, but we're signing all the inputs, we can use the same thing as well for this one BSV output. So this would be the same note. But if someone else wanted to say, hey, I'll give your daughter some money as well. So we've added another one and we've signed that with a sig hash all. It's going to undermine the first signed input, because when that signature was created, it was only created expecting there to be the one input. So now that we've added a second one, this signature will be valid, but this signature will be invalid because it didn't, the hash previous outputs is only going to be specifying one when there's actually two previous outputs being committed here. So yeah, we lock that previous one and unlock that one, but that makes the transaction itself invalid. So what we've got here is if we want to be, sequentially adding these inputs, we'll use the anyone can pay, and it links them together when we add the sig hash none on at the end. So this one allowed more inputs to be added. This one did, but this one says all the inputs have to be in their final structure, but we can still add outputs onto this transaction. We're adding that much in, but then we exceed the amount that's been committed to the transaction, and that's going to cause an invalid one. If we look at how the outputs are defined by these, so under this one, maybe this was a family that just got obliterated in Brazil and wants to do some crowdfunding, and then someone else finds another family and adds another input, and we're like, okay, we've got 3 families here now that we want to provide some funding for, and we'll go around and see if people can add inputs into this equation to create enough funding that it can be processed. So the first person says, yeah, I'll be willing to commit, but only if the money's going to go to those recipients. So they've done an anyone can pay, signing all the outputs, and they've locked it together, but we can still here be adding more inputs into the equation. And then the third party is like, yeah, we've got enough now. I'm going to put the sig hash all on there, and the whole structure is now fixed and the transaction can be processed. And I'm just simplifying this with no fees because it gets a bit unwieldy. And then the other flag that's interesting is the sig hash single, and that locks an input to a particular output of the equivalent index. So in this one, we've got one in, one out. So we've used a sig hash single, but still an anyone can pay. And then we can add another one after the fact, and this is still all valid until we sort of lock it all with an all, or even a none would have still kind of had an effect of locking all the inputs together. But if we've done something like we've got a anyone can pay single, and then we add another anyone can pay single, but we haven't increased the amount of outputs, because it only, when it does that sig hash pre-image creation, it's expecting there to be an output of the index position 2. And if there is no output, then it can't recreate the signature in the same way. And so that transaction's going to fail as well. So essentially what we've got with these transactions is an arrangement where you have almost like a trust level. So if you trust the party that you're passing it on to and you want to give them maximum flexibility, then you can use the anyone can pay, not signing any outputs. However, if you are passing it across, some adversarial state, then you can use an all to lock everything together. So with this input structure as well, I mentioned we've got this end sequence value, and that's in its maximum state. But if a transaction has an end lock time in the future, and the end sequence value as its lowest value, it can be sort of re-signed multiple times, so long as one of the inputs has a greater end sequence number, and the same inputs are used in the same ordering. So what this can allow for is these dynamic situations where you can pass content as like a push data payload in a transaction, and you're exchanging it between parties in multiple rounds before the transaction's actually going to be able to be mined by the nodes. So we've got it's not mineable till the 30th of June, and we can negotiate back and forward, putting in inputs, outputs if we're using our sig hash flags in the right way, and use that to, it becomes like the transaction itself acts as an escrow, because you can incrementally add a bit more data or whatever you're delivering through that, and you can request a little bit more payment, and when the payment was satisfied, you can add a little bit more to it. So no one's ever at risk, because if it's set up in the right way, I've simplified this as well here, because actually, to do it securely, you would probably set up like a multi-signature account where you're both party to, and you can, keep the other honest. But this is just to sort of simplify it for this presentation. But what happens here is Alice she wants to get some of these packets of the movie off Bob, and so she's sent through, 0.1, 10,000th of a Bitcoin, and then Bob goes, all right, I'm going to add one of these packets in the push data payload of an output and pass it across to Alice, and she's got it now. And she goes, okay, cool. Well, he came through with the goods. I'm going to now increment my end sequence by 1, add a bit more value to the output, and pass it back to Bob. And he'll, send some more data through. Alice is now getting more of these frames, incrementing the end sequence again, adding value to the output, and essentially, this clicker is a bit, it's going to go all the way through, and now Alice has got the whole transaction, all the data. So now, because we've never actually sent this to the chain, we're just passing it party to party, but we go, why should we pay a greater fee to have this data on chain? So what we can do, because we didn't sign that output ever, we can just remove it, add in the change address, increment the end sequence to its final value, and that final value of that input will override this and lock time in the future. And now the transaction can be broadcast to chain. Alice gets her change, Bob gets his 9/10,000ths of a BSV, and both parties are happy. And so then when that transaction's sent off, it goes to the node. The node's written their Coinbase transaction as their first one, adding subsequent transactions in and building out a Merkle tree in this fashion of all different, inputs, outputs. They're not being signed there. And when that Merkle tree creates a single Merkle root, and you hash that serialized header using a particular nonce value, and you generate a hash and it's unsuccessful, then you increment the nonce and you produce a valid hash. And what that does is it locks that Merkle root into that header, and that Merkle root securely summarizes all of those transactions in that order, and that's now going to be appended to the blockchain. So if we had a particular transaction, say the index position 2, the third transaction, and we wanted to calculate, can we generate the same Merkle root? You can be just provided those other values to get to the Merkle root. So we end up with this sort of payload of interior node values of that Merkle tree, which we can use when we're provided to create these calculated values and get to that Merkle root. So this is Bitcoin Unified Merkle Path format, which basically says these are the values in this way, and trying to represent it as a little, icon there. And that means when we've got our block headers, which are only 80 bytes each, so if you're storing a blockchain at 845,000 now, it's about 65 megabytes of data that everyone can just host locally. You can fit it on any low-powered device. And then you simply need to pass those Merkle paths. You store the Merkle paths of all your spendable outputs. So whenever you've generated a transaction, through a Merkle service, you keep the path for it. Or if you're past a transaction, you request an additional data envelope of that bump data, and you now have a mechanism with these spendable outputs and these SIG hash flags to use these peer-to-peer electronic cache notes that you can lock and commit to any particular structure through that flexibility. So we could think of then our, this is a small version of our spendable transaction outputs, but through like a hierarchical key scheme, we can, derive multiple keys from multiple keys, and that will be our, a bigger set of spendable transaction outputs. And that could represent not just an individual's, but it could be mapped to something like an organization. So this is a DAG, there's a president, he's delegated authority downstream, but they can't delegate authority back to him. So it's a one-way, there's no cycles in this, but those key schemes can be transposed over the top of that organizational structure, and you can start to use transactions as ways to like define data access schemes and such through your organization, or have file management, versioning systems. If you put it into a documents workflow through an organization. So what have we? Yeah, there are outputs with that structure and those flags. We can sort of think of that transaction container as something like a repository. If you're using Git, you'll stage changes before you commit the changes. So adding inputs that have been signed to the transaction, you've kind of got like a working directory first, which is your spendable transaction outputs for either you or your organization. But then I want to pass a document to another party that needs to be signed electronically along the chain. So I can sort of initiate that with a particular signed input by me, expecting them to add an output and sign it with their key that's associated to them. And then when the whole transaction's locked together by applying like a sig hash flag, a sig hash all, it's like committing the entire transaction. And then you could do something like a push to remote, which would be broadcasting it to the blockchain. So then if we think you've got your document there as a data payload to one of those spendable transaction outputs, you created it, you can define your access management. And then as you move it through these systems and different people add to it, it becomes like a versioning system where with Git, they use a system called a Merkle DAG. So it's a directed acyclic graph, and it's a Merkle tree, and values of the directed acyclic graph are combined at certain levels into the Merkle tree to lock states of an item into a fixed structure. But then you can use that Merkle tree and the Merkle proofs, or the paths, to find the hash of the document in a particular version. And if you store that against, in your local drive, you've got the different states that are mapped chronologically through an immutable proof with the Merkle DAG. So, it's just a different way of thinking about the transaction. So imagine you've got someone's placed an order for a product. The transaction, is the container's initiated. You add an input into it. You specify an output. The funds are going to go to Amazon or such. So you're collecting the money because you're signing the input going into it, specifying them as an output, but it's not locked. So then it goes through to the inventory. They might add something by its serial number, sign that as the store warehouse manager or something, and then it's shipped. And you can even involve other parties in it. So it's being delivered through FedEx or something. FedEx adds themselves as an output to that transaction, but it's not all fully signed. And then when the recipient gets their transaction at the end, they sign the transaction with an all, and it then basically says, yeah, now FedEx can be paid, now Amazon can be paid, and the whole sort of situation's resolved. But we didn't have a transaction and a transaction at each stage. We just used one that was being partially signed over its life cycle. So yeah, just hopefully, like, that information's all kind of embedded in our courses roughly, but it was a bit more of a single journey through it all. And that's really the end of the presentation. So thanks.
All right, thank you so much, Todd. Next up, we have Michael Buckley from TAAL, who's going to give an overview of TAAL's open source implementation of ARC, a service that is used for broadcasting transactions and ensuring that those transactions are received by the node network. Mike, welcome.
Hello. I'm Michael, the tech lead of transaction services at TAAL. And as it was already told, I will talk a bit about ARC. What is it? And how does it compare to MAPI, which you may already know a bit about the architecture. So how does it work on the inside? About the infrastructure that is needed to run it, and a bit about the roadmap. First of all, what is it? And it's not only MAPI 2.0. So Arc is a transaction processor, and it keeps track of the life cycle of each transaction, rather than just basically just forgetting about it. It is keeping it in memory, basically. It was meant once to be the successor of MAPI, which MAPI had a lot of problems, as you may know, and so Arc was in the beginning actually just meant to be an improved version of Arc, but that's changed later on a bit, but we will see why. And Arc is also operated by TAAL. Apart from Gorilla Pool, I think Gorilla Pool are the only other ones who run it at this moment. I think Kurt already mentioned it. And it can be operated in different ways. That was the one core principle of Arc from the beginning. It should be possible to run it on a single machine, but also on multiple machines or Kubernetes, as we do it at TAAL. So the product of Arc is actually owned by BSVA, but developed by TAAL right now and also operated. And so we do really a lot of updates, or we deploy very many times. So in this way, we ensure that we always have we run a version which has the latest improvements. Let's look at the life cycle once. So one important step is the validation of the transaction in the beginning, like checking the UTXOs, so the inputs and outputs, verify the signature. Once that is done, we say that this transaction is received. After that, we store it in Arc, and then it's stored, has a stored status. Then the transaction will be announced to the P2P network. So it gets the announced status. If any node will request that transaction, it will be requested by network, and then of course it will be sent, and afterwards it can have multiple different statuses. So if, for example, the node sees that this transaction has no inputs, then at first it will be seen in orphan mempool, which doesn't mean it's rejected. It just doesn't have a parent at that moment. The parent could come later on, and then the input is there, the parent is there, and that would mean that it will get out of this status and will be accepted. So there is a missing line here. But it could also be rejected if, for example, it's a double spending transaction. So if it has been accepted, then so Arc is waiting to see the inventory message from another node, and then only it is seen on network, which means that the transaction has been broadcasted. So that's like the proof. It has been received from another one, so that means obviously it was broadcasted. And then basically Arc is waiting until it knows that it was mined, but we will see how it does it. So maybe a bit about the history of this project. It was started in September 22 by Sigi and Simon. They're both here. And about half a year later, they moved on to another project. They started to work on Teranode. And so then me and later on my colleague Shota Silagazze took over. Then there were a couple of things that we had to do in order to make Arc scalable. But there were also some requests already from users. There were some users who already gave us some suggestions. For example, one user needed very much the feature that when you submit a whole batch of transactions, that it should be possible that they are chained inside of them, and this we then delivered as a new feature. Then in September 23, it was officially declared a public beta, but we were not finished with Arc then. So we had a lot of work in order to make Arc scalable. So we had to containerize it, orchestrate it, and finally we started running on a Kubernetes cluster. But still, that was not all that we had to change. You will see later on, we also implemented a message queue for the different services that are running in Arc. There are not many services, but for certain cases, it was much better to use a message queue than gRPC calls. And then finally, in April 24, just recently, Arc was released in version 1.0. At that moment, we tested it with 1,000 transactions per second, but I'm sure we can go above that. There are certain limitations to our still to the tooling that we use to do this test, but I will tell a bit more about this. So comparison with MAPI. First of all, one thing that Arc does and MAPI doesn't is Arc does retry transactions. So if it could always happen that the Bitcoin node could somehow lose a transaction. In theory, Arc will keep it in memory and just announce it basically until there is a node which requests it, and then it will send it. So this is this mechanism was also from the beginning we had it. Then this transaction lifecycle, I already showed it. It was built to scale. So as I said, it should be possible to run it on a laptop or a Raspberry Pi if you want, but also on a Kubernetes cluster. Then the biggest or most important difference probably is the how does Arc communicate with the node? It doesn't use RPC calls like MAPI did. It uses the P2P network directly, and that is a big advantage because it also makes Arc basically future-proof for the Teranode world, where we will most likely not have any RPC calls. And also we have the extended format. I'm not sure if you know about it. So that's we already just in the last presentation saw the transaction format in a bit more detail, but there is also the extended format, which basically also includes the locking scripts and the satoshis of each input, and that allows Arc to basically validate the signatures without asking each time the node again, which would then require again RPC calls. So we in order to avoid the RPC calls, we need that extended format. And as I already said, so we have the capability to actually send a whole batch with chain transactions to Arc, and it will basically be, if they are all valid, they will be mined finally. This was not possible, I think, with MAPI. Quick comparison of the two formats, how the flow is of the like the activity flow. So the standard format basically checks for each input again the Bitcoin node and asks for the input, and the extended format doesn't need to do that. So Arc still can use RPC calls, but it's just possible. I mean, if you need to submit the standard format and you can't for some reason use the extended format, so that's much faster, of course. Then quick overview about the tech stack. So Arc was written in Go. I wonder how many people here do program in Go? Not so many, but good, cool. we have a Docker image of Arc, which we publish on Docker Hub. We use the message queue. So the implementation of the message queue was done with nuts.io. I don't know if you know about that. That's a nice technology that we discovered. By the way, nuts is also created in Go, so it was super easy to integrate. Then inter-service communication still with RPC calls, gRPC. Data storage, we have only one implementation right now. So Arc obviously needs data storage. It uses Postgres. There used to be more other available integrations with, so BadgerDB, DynamoDB, and SQLite. We unfortunately at some point had to remove them because it's just slowed us very much down at the development. So they could come back if somebody needs it. I mean, if there is really a big need for it, we could always bring it back. Okay, here's a little overview about different documentations that we have. Maybe it's a bit too small for you to see, but anyway, there is a developer documentation on Git, on the GitHub repository, meaning it basically explains how you can run as a developer Arc and what are all of these different CLI commands. Then the high-level documentation is also on GitHub. The Docker image itself has a bit additional information, and then TAAL has TAAL who runs Arc has on top a bit of documentation because at the moment you don't need it, but in the future you may need to use an API key to submit your transactions, and that will be explained there. A bit an overview on how it's working and what is in there, what is in Arc. So we have an API service which does the validation in the beginning. So if it's not sent in, the transaction is not submitted in the extended format, the API service will ask for these inputs through RPC calls from the node. It will check for the fees. So Arc knows the policy of the nodes which it is connected to, so it can also check if the fees are enough. This check you can also override with a special request header. Then the script is checked for validity. Also, this check you can override if you want. The size, the input. Then the most important one is Metamorph. That's the that's the service which actually is communicating with the nodes. So it submits transactions to nodes, it stores and updates them, and then finally, which is important as well, it's a feature which was there in MAPI, but we also have it in Arc, is the callbacks. So for each transaction that you send to Arc, you can give a callback URL, and then you will be informed asynchronously about status updates. And BlockTX is the third service that's running alongside. It is basically listening to any blocks that are being created. It stores this block information and calculates Merkle paths for all of those transactions that have been found, which are submitted through Arc. Not any, but just those. And then there is the broadcaster CLI. It's just a tool that is also in this repository. We use this tool for performance testing. So a short overview about the architecture. So in the yellow boxes, you see these three services. So basically, a transaction is submitted to the API, it's validated, comes to Metamorph, and then through the message queue will be sent to BlockTX. So it's published here, BlockTX. I mean, any BlockTX, it can be multiple BlockTXs running. will take it and look for it basically in all the new all the new blocks that are being announced. And once it has found it, it will publish that, and finally Metamorph can update it on the storage and sends the callback if it has to. We also have a ZMQ connection to the nodes. That is how Arc basically finds out about rejection because of double spending or missing inputs. Yeah. Now a bit short overview about the roadmap. So new features that Arc could have in the future. There is one which is the BEEF format, the background evaluation extended format. It is basically an even more extended format than the extended format. It includes more information, and also so it allows for streaming validation, so that while the format is being submitted, you can already validate it. It's already in progress, so I think this we will very soon have. I'm not the expert on this, so if you have very technical questions about it, Dagen is your expert on this. Then of course Teranode, which is on the horizon. Arc has to work with it. For example, so there will be some integration work. As I hear, for example, so ZMQ will not be featured in there anymore, so Arc has to be updated in this way. One more thing that was that is discussed or could be done in the future is a separate service just for Merkle calculation. At the moment, this is done in BlockTX, but if it could be outsourced in case that this is not a good enough architecture anymore. If it doesn't scale with very, very big blocks, for example. Short overview about TAAL. What does TAAL do with Arc? So it runs it on a Kubernetes cluster, as I already told. So just to, what does it mean in reality? It means, so each of these services can scale by itself. So it can have one pod, or it can have 1,000 pods basically. And it's scaled automatically with the transaction volume that's coming in. Also this message queue here, which I told is a pod which can scale. Yeah, so that's happening. That's basically very automatic already. We have also some topics on the roadmap. So what we've been working on a lot was the monitoring part, basically the tracing metrics and alerts. So Arc is we want to know first if something unusual happens, like a transaction is stuck for too long in a certain status, which would we should be informed about it, and it could be a bug or whatever. We need to know about it. So this is already in progress or mostly done. Then we have few topics for the future. Possibly if this nuts IO is not good enough anymore at some time when we have then 1 million transactions per second, we may want to use another technology like SQS from Amazon. And one other topic would be the custom load balancing policy, which is could be a bit a smarter way how to balance load between the pods. At the moment, it's just a round robin. Yeah, I'm not sure if these things will also be open source. That's rather up to my colleague Ernesto, who can't be here. He's the product owner of Arc, of TX services. So this you can forget. It's just some quote. And yeah, before I say thank you, I forgot a few things in the slide. So I also want to mention so the Kubernetes infrastructure is also open source. It can be, it's a bunch of Terraform definitions, manifests, I think. Yeah, we forgot to put it in the documentation. I should do that shortly. But this is also open source, so anybody could run ARC the same way as we do. The other thing I forgot is we have a Discord channel. So BSVA has a Discord channel for ARC. Any new features that are desired or requested would be probably good if you have an idea what we should add. I think that's the right place to ask for that. And also TAAL has a Discord channel where if anything is broken or whatever, that would be the right place. Yeah, that's it. Thank you.
Very much. I appreciate it. Okay, everyone. When I say Darren, you say Kellenschweller. That one's not going to work nearly as good as the Ty Everett Project Babbage bit from earlier, but let's not hold his long name against him. Friends, welcome to the stage, Degan, Thomas Giacomo, and Jake Jones, followed by a presentation from Siggy Oscarson.
Good afternoon, everyone. Today we're going to announce the Mandala upgrade, which is basically an upgrade of the BSV network to adapt the new network topology to Teranode. Right. So I'm going to start with a quick introduction of about what do we mean by the Mandala upgrade, and then Darren will cover the SPV wallet reference implementation, Jake the overlay services, and then Siggy will cover Teranode. So the term Mandala is actually inspired by a biological network with high connectivity and low distance between different stakeholders. The reason why we chose this term is that it describes the way the BSV network will be constituted. As you can see here, at the center of the network, you have Teranode, which constitute the core node network, and then on top of which you have overlay services and SPV wallet. This network topology allows Teranode to be highly scalable, just to deal with standardized transactions, and then all the business needs and all the specialized environments will be taken care of by overlay services to really allow a peer-to-peer communication at the edge of the network with SPV wallets. So that's the reason why we need this upgrade. Is we need these three components. We need at the center a standardized Teranode, which will deal with standardized transactions, overlay services, we're going to deal with different business needs and specialization, and at the end, SPV wallets, allowing real SPV implementation through peer-to-peer communications. So why do we need the Mandala upgrade? The simple answer is that the current network topology is not aligned with Teranode, and if we release Teranode, nothing will work, right? We need to adapt the entire network to the Teranode era, allowing the entire network to scale and different applications to leverage the capabilities of Teranode. So as you can see, today there are only 2 layers on the network, and as there are only 2 layers on the network, we don't have a dedicated layer to deal with the different business needs and specializations for the different use cases. We are not able also to really leverage the SPV and the section 8 of the white paper to allow peer-to-peer connectivity and peer-to-peer communication at the edge. And the current node software, SV node, has some current limitation related to machine spec and different settings. Finally, we have on the network some listening nodes, and these listening nodes, as they are not incentivized to upgrade and to invest in the different node upgrade, they decrease the efficiency of the network that other mining nodes are incentivized to proceed. So these are the current limitations of the network, and that's why we need an upgrade of the network through what we call the Mandala upgrade, to have again at the core of the network Teranode, the new node software updates, and then on top of which you're going to have overlay services to deal with different business needs and different specializations, and at the edge we're going to have SPV wallet, which will implement the section 8 of the white paper and SPV to allow peer-to-peer connections. So I'm going to stop here. I'm going to let Darren explain you in detail the SPV wallet reference implementation, and then we're going to dive into overlay services with Jake and with Teranode with Sigi. I hand it over to you again.
Thank you, Thomas. Put your crash helmets on, folks. We're going to take this at breakneck speed. SPV, the general idea is that you should be able to validate transactions when you receive them. Now, currently the model is use all blockchain data and grab one of the transactions from it using some sort of filter. This makes me angry because it's expensive and that's a lot of data and you just want this little transaction to be verified. So what do? We do script evaluation. We sum the Satoshis in and make sure that there are more than the Satoshis out. We must make sure that each input is associated with some sort of real UTXO, i.e. there is a Merkle path and there is a place where it is in a block. And we check lock time and sequence. I'm not going to go into that just now. It's not important for the presentation. So we have a transaction, we have its Merkle path, we have block headers. Where do we get those block headers? Well, we get it from something that serves as block headers, a block header service, of course. So we connect to the peer-to-peer network, that's the nodes. It retrieves all of the headers from back to Genesis all the way to now, or at least 10 minutes ago. And we have an API to check that the Merkle root at any given height is a specific thing. So those are the things we need to check. So this is a block, this is the tiny header data. What's in there? Previous block cache, Merkle root. There's a bunch of other stuff that miners care about. But the point is it's easily verifiable because it's got a bunch of zeros at the end when you hash this thing. So if you hash all of that stuff, it's going to have a bunch of zeros. And if it doesn't have a bunch of zeros, it's probably fake. Because that's what costs money. That's what requires ASICs. And this little header is what actually gives us the blockchain. It's the hash chain of all the headers. We go back again, because this one points to the previous one, and the previous one points to the previous one, and so on and so forth. So it's a hash chain. That is the blockchain we're all talking about. It's in the name, BSV blockchain. The other thing of interest was that Merkle root. So how do we get that Merkle root? Well, we have a transaction because we literally are holding it, so we can get the TX ID, which is just a hash double SHA of that particular transaction. And all these other things are just the other transactions in that same block. And so we can hash together these yellow things, which we call a Merkle path, and we get a Merkle root, which proves that that thing is in some blob there, and there's no way to fake that. So we check against our chain of headers, and we see that one of these chains has a Merkle root value that matches, hopefully. And if it does, we know for sure that that transaction ID is in that particular block. So we now have minimal data required to prove the inclusion of that transaction in some previous block. With 68 megabytes to date, that's 850,000 blocks, 80 bytes each. We have a Merkle path, which at Teranode scale would be about 1.5 kilobytes. It's a lot smaller these days, but let's just hypothetically assume that that's going to happen someday. And transactions on average something like 570 bytes, so tiny, tiny stuff. So the only problem is this thing only appears on average after 5 minutes from broadcast. So what do we actually do real world when we're doing SPV? We have to attach source transactions. So we actually only have the Merkle path for the previous transaction or source transaction. This is where Beef enters in. So thanks, Mickey, for the intro to Beef. So it's BRC62. If you want to check out these details in your own time, it's brc.dev/62. Background evaluation extended format. So really all it is a bunch of normal transactions and a bunch of Merkle paths for some of them, and then just like pointers to which Merkle paths point to which. So here's an example. So we have the version bytes, which is why it's called beef. So when you're looking at it as a developer, you can quickly identify what format it is. The blue thing there is the Merkle path. The pink thing there is a parent or source transaction. And then the little 1 and 0 there just points to that being the Merkle path associated with this particular one. So if there were many, you'd have pointers to the particular Merkle path for each transaction. And then you have the transaction that you're trying to make or trying to validate, rather. So this is the white transaction here. And of course, the transaction has a list of inputs. And this is the first input. And that is the hash, the double hash of that. So that's how you link these transactions together. It's the transaction tag. So that's what you're checking in real world. So those green arrows are just links, previous outputs, source transaction, and so on. So anchoring works in a long chain. So you can imagine in this scenario, we just have a Merkle path for the pink transaction, and it has a child transaction, the blue one, and that has a child transaction, and that's the one that we're trying to validate. So as long as we can either check the entire previous transaction or a Merkle path, we don't need to check this one's parents because we know it's valid because it has a Merkle path. If it didn't have a Merkle path, then we would need to check its parents as well, and the chain would continue. This is not a huge amount of data. So if we know that's valid, then we know that's valid, and so on and so forth. So most people are thinking at this point, how do we check that the current spending inputs are not already spent in some other transaction? And this is the contentious slide. Alice and Bob have some sort of digital relationship in that they're exchanging data. So these two together, let's just say Alice is giving a transaction to Bob. Between them, they know for sure whether or not the transaction inputs have been spent, or the previous transaction outputs. So if Bob is doing the validating, okay, he doesn't have access to that information, but Alice does. And there's a whole scenario that has gone on in sort of real world transactions where you're either in front of someone paying them as a merchant, or if you have an internet communication, there's some establishment of identity before you're sending this transaction. So it's not that we don't know at all, it's that the sending party knows for sure whether those outputs are spent. And so we use the legal system if there are any disputes, but because all of that exists, we don't actually take someone to court for a simple spend. It's just a case of no one would do that because within a second of broadcast, Bob would know. And so why would Alice waste anyone's time with that? So there's none of this sort of basement dwelling, well, we have to check the whole block just because, we have to send a transaction and wait for block confirmations. That's all nonsense. We have all of the information we need to validate that transaction immediately. And that's how you have safe instant transactions on BSV. So how do we do that in code? Well, we have the TypeScript SDK now. So it's 2 lines, verified, done. It's very easy, but let's go into that a little bit more. So we need a chain tracker of some sort, which is a class that really just validates whether or not this particular transaction ID appears in a particular or rather, this particular Merkle root appears at that block height. That's all that checks, really. And I realize this is quite small for the people in the back, so I'm not going to spend long on this. But really, we check that the input scripts validate with the output scripts of the source transaction. We check all of that unless there is a valid Merkle proof, in which case we don't have to run this script validation at all. Assuming we do, we run it here in this spend script here. And that's the thing that calculates the pre-image that Todd was talking about earlier and validates all the signatures or whatever unlocking conditions are required. And this would be the internals of the header client that was passed in. So just a root and a height just looks up something that checks that that's the root for that height. Easy. True or false. Same thing for the gophers. I think there was about 4 in the room, so we can swiftly go through this. Same idea. List of transactions. You validate all the scripts for all of the ones that you don't have Merkle paths for. And if you have Merkle paths for them, then you can just verify that the roots are valid. And again, same idea. The Go one actually does a slice of multiple so that you can do them all simultaneously. So it's a little bit more optimized in Golang. Okay, so this is the SPV wallet architecture. So this is the thing that's in public beta now. You can grab it at docs.bsvblockchain.org, and you'll see the instructions on how to spin this up locally or deploy it on AWS quickly. One notable mention is we also had a NPM package put together, NPM install at bsv/paymill. If you're another wallet, then that is how you can be compatible with all of this stuff. So it extends Paymill a little bit with one particular extension. It's backwards compatible with Handcash, works with Rock Wallet these days, and it works with all of the sort of Paymill endpoints that existed previously, like P2P destinations and receive all transaction. It doesn't do basic address resolution. So it's the Paymill server is not going to give you just an address. Because that requires global listening, don't support that. So we're full SPV. So if you used Mr. Z's handy tool, the Paymail Go CLI, you can do Paymail capabilities and then a URL of whatever your deployment is. You'll get a list of the capabilities here, and that's the beef one. So that's the only new one. It just would use P2P payment destination to get outputs as normal, and on the second call, when it's delivering the transaction, it would be expected to deliver the beef transaction format. So what have we got at the moment? We have a web wallet front end for the SPV wallet. The team is working, the 4Chain team is working on the mobile React Native client. We have a white label browser extension wallet, which some people in the room, Dave is working on soon. We're going to kick that off soon. And a desktop wallet is, we'll see. We'll see how that goes. There's a couple of suggestions there from various developers that are keen to do that. So let's see how that goes. But some of the features, so I wish I had the demo for you today. We'll have to do it in a later sort of publication sometime. There's a TOTP trusted contact setup. So, you know, I said Alice and Bob, and there were green ticks next to them earlier. So that exchange that you would need to do in person doesn't have to happen because you can see each other. But if you're contacting someone through a Paymail server and they're on the other side of the planet, the only reason you know that they are the person they are claiming to be is we can use some crypto stuff, some elliptic curve stuff to prove they are who they say they are, kind of thing. So just like you TOTP into your bank, you could TOTP into the counterparty and set up a trusted contact like that, even if they were remote. So you do that for each other. There's a couple of things. There's a patent filed on linked key solicited payments that's associated with the wallet. That's coming as well. And then we want to do in-person, offline P2P transactions market in Kampala. So those are the sort of ongoing sort of projects, features coming soon, and of course token support using overlays, which Jake will get into after me. So my last slide here is just on services. So we've spoken about extended format a number of times today. We've spoken about beef twice today. If you don't have those things, you just have normal transaction format. So say if you're using any of the existing wallets and somebody sends you raw TX, then you don't have the data because they never sent it to you. Use a service like this to go get that data before you then broadcast onto Arc. So for the left, you would use that for Arc broadcasts. Or if you wanted to do SPV, despite the fact they didn't actually send you that data, you could use that, which uses WhatsOnChain to go grab the data, sticks it into the correct format, and then you can just do .verify, and you've done the check yourself. You've done SPV, and it's fast. It's just Vercel APIs. So very quickly now, transaction lifecycle. So Alice is sending her transaction to Bob. We're going to pass that on to an overlay, which Arc is an example of a sort of proto overlay. It's a generic overlay that will accept anything. That's going to pass it on to Teranode. Don't ask questions about how that happens yet. Teranode eventually minds it, has a Merkle path calculated, passes it back to the overlay because that's where it got it from. The overlay would associate that with Bob because that's where it got it from. Bob would say, "Oi, Alice, here's your Merkle path for your change outputs. Thank you very much." And then everybody is happy because they all have green transaction dots next to them. And thank you so much. I'm going to pass on to Jake, who's going to explain overlays.
Okay, so raise your hand if you've heard the term overlays before. Okay, yeah, okay. Everyone's just kind of wondering what they are, eh? So, well, an example of an overlay is augmented reality, like this picture is showing. It's essentially just some kind of information that's overlaid on top of some kind of an underlay. So in augmented reality's case, the overlay is augmented reality and the underlay is reality. So we're taking this concept and applying it to Bitcoin as well. And the reason we're doing that is because we want to make sure that Teranode only has to do the actions that are laid out in section 5 of the white paper and nothing else. Because right now, as was explained by Tomas and Dagan kind of touched on it too, it's the network can't scale if Teranode is doing too much. So an overlay sits on top of Teranode, which is an underlay, but that's not really the best way to describe it. It's more like transaction types. It comes down to transaction types. So you have a base transaction type that Teranode understands, and then you have specific transaction types that different overlays understand. And so those different overlays can talk to SPV wallets, and they can talk to each other, and they'll understand what those transactions are, but they'll filter out other transactions that they don't understand. And so it shifts the network from being a purely computer network to more of a semantic network. And so if we look at this, current assumptions right now, this is touching on the fact that nodes are doing too much again, is we're able to get this data from a node. So a node is not only mining, but it's also taking care of supplying data and lookups and that kind of thing, which obviously doesn't scale. And so what an overlay does is it takes advantage of SPV to reduce this. So if we think about it this way, the yellow dots are one overlay, so that's one transaction type. The green dots are another one. And then the red dots, so these are including payment tokens. There we go. And so you have all these different transaction types, and they're all the same base transaction type. So Teranode or nodes understand all of them, but not all overlays understand all of them. So if we take a closer look at the structure, so we have inputs and outputs, the yellow inputs, yellow outputs, green inputs, green outputs, and then the red is understood by both. And you can see how it shifts from being a purely computer network where you have devices that are attached to a network. So if you think about it from an IPv4, IPv, like a LAN WAN perspective. So a computer network is like your local area network, your wide area network. All of those devices are connected to each other via that network. And so if an attacker gains access to that network, it's crunchy shell, they gain access to everything in the network. And so this shifts things to an individual device model. So now instead of being part of a computer network, that becomes agnostic. You don't really care which network or how that information gets transferred. It's more related to what each device understands. IPv6 is a really important part of this too. So just really quickly, this is some features. So you have ingestion, validation, maintenance. This is also just adding to the fact that we don't want nodes doing everything. So it's shifting the responsibility of nodes in maintaining transactions down to overlays and overlay networks. So instead of having a global view, now you have an overlay view, depending on what that overlay data type is or transaction type is. I'm speeding through this really fast too because I only have 12 minutes. Sorry. So you have, yeah, We don't need to talk about that. Okay, so here's an example of what you could use to build an overlay. Web API, so that's how you talk to it, and then you have a store, which stores UTXOs, the headers, the Merkle paths, and transactions, really important. And then you have the validator, which is checking not only that it's a valid transaction, a valid base transaction, but it's also going to be checking that it understands it as part of its overlay. So it's doing some additional checks. And this can be like a hash in the version field of a transaction, or it could be the format of the transaction. So it has certain things and certain outputs. And maybe you have, like, you could do a SHA-1 hash maybe in like the first output, because it's safe enough to use for something like that. And then you have the rest of the data in the other outputs. There's all kinds of ways you can approach this. But the key idea is you're getting away from having nodes having to deal with everything, and you're shifting things down into more of a specific view. The other pieces here, so we have a listener that's listening for rejection messages. Multicast isn't implemented yet, obviously. And then the path confirmer, so part of the Merkle service, as Dagan was explaining. So here's what things look like right now. So you have SPV wallets submitting things through the API, validation, UTXOs get updated, things get broadcasted through Arc possibly, even though Arc is kind of an overlay. But that's an important point too, is overlays can talk to each other. They don't have to be stuck within just their own network. At the same time, they're also responsible for their own data. And so this is the same thing with IPv6, but I want to take you through a quick example. So if you imagine this is a ticket distribution example. So you have a ticket issuer, ticket distributor that generates a bunch of event tickets. And then what they're going to do with these event tickets is they're going to tag them to specific tranches. So you have the first tranche, which is one transaction, and that has a number of tickets in it that's connected. Each ticket is connected to an output in the transaction. And then you have a hash of the ticket connected to each output. And so once those are created, they can be sent down to merchants or sellers, and it's just a simple transaction from there. So the output goes to an output that one of the sellers or one of the merchants control. And as long as you send the hash along with that, maybe you set up a format where you have the hash of the ticket in the first output, and then you have the combined output in the second one. So what you would do is you would take the hash of the ticket, and then you would take your public key and you combine that in some way. You can either do that by hashing, or you could turn them into big numbers and add them together, multiply them, XOR them, a bunch of different ways you could do that. As long as you have some kind of a deterministic unique identifier that the receiver understands, and you have the supporting information that they need in order to send a subsequent transaction. And so the sellers get it, and that's pretty cool because you have a little bit more specificity here. And then they're going to sell it to some event goers, some customers. And here's where it gets really interesting, because they can do the same thing and sell it to those customers. But as Todd was talking about earlier, you can do some fancy things with things like sig hash flags. So you could use sig hash none, anyone could pay, so that the outputs aren't signed. You're only signing the inputs. And then that seller could resell the ticket, because it doesn't really matter who has the ticket. It's when they get to the gate, that gate needs to be able to understand what that overlay transaction type is. As long as they understand it, it's fine. And then the history can also be captured within the transaction too. So you have another opportunity to gather data. So this is just looking at the different attributes. So you have the issuer, they're managing the overall inventory. And then you have the merchant, the seller, and each of them is handling their own set of the inventory. And they don't need to sync with each other, because those transactions, those tickets were created initially, and they're being transferred along with Satoshis. And so we're leveraging the network and the double spending protection of the network and all of the benefits that go along with that. And we don't have to do extra work around that, we can just take advantage of those things. I don't know what I'm like for time, but that's all I had. Hopefully, some questions.
All right. And next up, we have Siggy Oscarson, who will be sharing a overview of Teranode. Siggy, welcome.
Thank you. Thank you. Thank you. Hi, guys. I am Siggy. And just to start off, if you read this as fast as Degan was talking, it's going to be a little bit less. But if you read this very slowly, we're processing about 50 million transactions while we read this sentence. And just to put, we're just trying to put into context what we're doing here. This is actually mind blowing. We're blown away every day by the volume of transactions we're processing ourselves in Teranode. And I took a screenshot of our Grafana dashboard just yesterday, for the last 2 days, and we've been above 1 million transactions a second for the whole 2 days, with some dips, which are actually when we're processing blocks, but it seems to be working. What we've been doing for the last year has culminated into a thing that actually does 1 million transactions a second. It's amazing. It's just... But there's a lot of misunderstandings about actually what we're doing. So what we're doing is rebuilding the BSV node from scratch with unbounded block size. And there was some things that seeped out in the marketing that I probably shouldn't talk about, but I'm going to do it anyway, that were called the UBSV, the unbounded BSV blockchain. There's nothing different. It's just an internal name that we used, but it signifies that we're unbounded. That's what we're trying to build. We're trying to build something that if you throw 2 million, 3 million, 4 million, 10 million transactions a second at it, the architecture should be able to handle it. You should be able to scale up. So we're really going for this unbounded thing. Is 1 million transactions a second is just the first step. And we have to do that by horizontally scaling everything. We're not completely there yet, but we're getting very close. One of the misunderstandings of what we're doing is, are we forking? Are we doing something different? We're not. It's just an implementation, a different implementation of the SV node. So it's fully adherent to the white paper, just like the SV node today, and it will create blocks, it will process transactions, do everything exactly the same way as the BSV node does. It's just a new implementation that scales horizontally. And something that we talked about at the beginning of this project is that Teranode only focuses on the core functionalities of a node. So there's a lot of things that happen in the Bitcoin space, in the BSV space, in all these spaces. And the nodes are actually doing a lot of the heavy lifting, and we're not going to do that in Teranode. The Teranode, we're focusing on processing transactions, spending the UTXOs, updating the UTXO table, and creating blocks. That's what we do. Everything else, we're not going to do. And that's why the overlay nodes are so important. These features that you're used to now to be able to go to the SV node, like the RPC server or something like that, that is something that we are actually going to build, but we're not planning to do it. It's not something that you should be relying on. So it's just the core functionalities. And so maintaining the blockchain, receiving and validating transaction, assembling blocks and validating blocks. That's what we focus on. And again, this is why the overlays are so important. So if you're building an application, you're doing something, you should start building that against those overlay nodes like Arc, and Arc will then be adapted to the new world of Teranode, and you'll be fine. You won't notice. The architecture. So what do? It's a microservices architecture, of course. And the core services of Teranode are eightfold. There's a propagation server which basically accepts transactions from the network. So it could be via IPv6, it could be via gRPC connection with HTTP endpoints. We have a lot of endpoints actually to accept transactions. And to be honest, this is a little bit in flux still. How the final version is going to do this is still not decided. IPv6 is the multicast is the preferred solution, but it's just not supported by all the ISPs out there. So that's not feasible yet. Then we have a transaction validator, which, like the name says, actually validates transactions, checks that the UTXOs are spendable, spends them, and then creates new UTXOs from the outputs. Block assembly, where all those things come together, all the transactions come together to form a new block template that the miner can actually mine against, and the block validation service, which we're getting blocks from the outside and you validate those. So you're getting blocks from other miners and you need to validate those blocks. So it's a completely separate service. And something I'm going to talk a little bit more about later is the subtree validation. We're not changing the block format. The block format is the same, the transaction format is the same, but we have created an abstraction of the block. And so we split a block into chunks of subtrees. And I'll talk a little bit more about that in a later slide, but that is one of the services where we are getting subtrees from other miners and we're validating them in real time. We have something called the asset server, which is basically used for from other miners to get things from your node. So it's a HTTP server that's just giving assets out. So that could be a subtree, that could be a block, that could be a transactions that are being requested. And we decided to do that using very standard technologies. So it's just an HPC server. So a miner could use standard tools from Cisco systems, from somebody else like Nginx reverse proxies to actually speed that up. That's not part of the Teranode itself, but it gives miners a lot more options than today to actually optimize this itself and get a little bit of advantage what they're doing. We also have a P2P service, and this is not the same P2P service that we have now. This is actually a new P2P service using libp2p, and it's propagating the Teranode type, so the abstract block and the subtrees, rejected transactions, and things like that. This is a screenshot of the architecture diagram that is up. Just to I don't want to go through into this detail, but just to give you an idea, is that the service has all been split up and there's a lot of chatter between them. There's a lot of talk. So you get this SV node, this is a monolith, exploded into different services. And this was actually hard to get this working at 1 million transactions a second. Because 1 million transactions a second, all these lines here, there's multiple million things happening per second. And the networks actually don't like that. So it was a lot of, actually a lot of the delays that we had in starting the test have to do with those tiny little lines between all the services and not the services themselves. Data stores. We're doing something a little bit, I think, different than SV Node does. We've actually, there's a couple of data stores. We need to store blocks, we need to store subtrees, we need to store transactions, we need to store lots of things. And we've created interfaces for every one of these things, and we've implemented multiple interfaces. Which ones exactly we're going to be releasing into version 1 is not decided yet, but you will, as a miner, be able to choose the technology that you're most comfortable with to use as a backend. And the 4 stores we have for transactions, UTXO, subtrees, and blocks, we have different backends for it. We're using Aerospike, which is an amazing database for the UTXO store. But we have our implementations. There's an S3, there's a Minio, there's a Postgres adapter. You can't use all of them for everything. So Postgres is not used for subtrees because those are big blobs of data, for instance. But you get the idea. We're trying to make it very, very flexible and also extendable for other people to implement their own. Other services that we have a legacy P2P network, but this is actually the old P2P network that Bitcoin runs on now. So when we start up Teranode later this year, hopefully, it will have to talk to all the other SV nodes on the current network, and that happens over the P2P network. So we need to have a bridge to that. We have a P2P bootstrap service that's not very exciting, but that's just to bootstrap the Teranode stuff, and we have a Coinbase overlay service, which is for miners to keep track of their Coinbases, all the blocks they win, they keep. That's a simple service. These are not very interesting, actually. So things. This is interesting. The subtrees. So one of the most important ways for us to scale this up, because if you're doing 1 million transactions a second, which is mind-blowing, you get, in 10 minutes, you get 600 million transactions in a block. And those blocks are over 100 gigabytes. So if you have to transport that block to all the miners, to the whole network, when you mine that block, that might take a long time. And so the miners, and that's actually bad for you as a miner, because the other miners have to first get that block, validate that block. It takes a long time, and then they will start mining on top of that block. So it might take a long time before actually they accept your block. In the meantime, they might have found block themselves in the fork you are. of the chain. So that's not a good thing. So what we want to do is we want to have continuous processing of everything that's happening. We want to get that 10-minute batch time, something big happens, we want to get that to be continuous. So that's where the subtrees come in. So what is a subtree? We talked about the Merkle tree a couple of times now. That's actually worked in the Bitcoin. Some other people have talked about that. And if you look at a graph like this, imagine that the data set, these are all transactions. And we take hashes of the transactions, the transaction ID, and we take hashes of that, until we get to the root. That's the Merkle root of a block. But if we say, I'm just going to take a certain size of a list of transactions, I'm going to define that as a subtree. This needs to be a power of 2 to actually work. So in Teranode, we have 1 million, so 1024 times 1024. And each one of those blocks, I'm going to send that immediately when I've when I got my transactions into my block template. I'm going to share that with the rest of the nodes immediately when I fill it up. So every second, all the nodes are sending 1 million transactions to each other, transaction IDs, which are actually not too big, it's about 32 megabytes of data. And they can validate if they've seen those transactions. If they've already seen those transactions, they already validate themselves. They can just do a checkbox, it's fine. This subtree is valid. And if they haven't, they can request it from that node to the asset server, which is basically a simple HTTP call to the other server. But when a miner has shared all his subtrees, so he shared 600 subtrees with all the other miners, they've all validated them, they've all been blessed, as we call it in Teranode. When he mines this block and he sends out the block a definition, it's basically the 80-byte header of that we talked about a little bit earlier, the block header, and a list of subtrees, a list of subtree hashes. So the IDs of these subtrees. And in this graph, if you have a block like this, these two things, this one and this one would be the subtree hash. So this subtree has this subtree hash, this subtree has this subtree hash. And the only thing you have to send is the block header and these two IDs. And you can actually hash this back into the Merkle root, so you can actually check if it's correct or not. And I know I've seen all these subtrees, I've validated them, so I'm actually done. So because we've been sending these things every second while we're mining, the pre-validation of a block is extremely fast. And this is how we get to 1 million transactions a second. Another thing that's interesting here is this is kind of replacing, I don't know if it's getting a little bit too technical here, but in the peer-to-peer network on Bitcoin now, Bitcoin sends inf messages to other nodes, tell them about the transactions that they've received. I received this transaction and tell everybody I'm connected to I have this transaction. We do that through the subtrees. So we're not just announcing all the transactions that we have, but we actually use that later also in the block validation. So it's like a double whammy benefit that we get from these subtrees. I think I'll have to leave it at that. Don't want to get into too much detail. So there's a paradigm shift in the network. And this is, I think this is something that could be contagious. We are changing the way the nodes talk to each other. And that we have to do that to be able to support this real-time sharing of a lot of information that's actually used in the block validation. Is that a protocol change? We think not. The protocol is the way the transactions are set up, the way that the scripts run, what the opcodes are in the transactions possible, the way a block is created. So the block is basically a list of transactions hashed together into a header. That's what the protocol is. The white paper talks about the transactions need to be shared. So if a node knows about a transaction, it should send it to all other nodes. That's what honest nodes do. That's what we're doing. It doesn't say how to do that. So in our mind, having the subtrees doing that is fulfilling the white paper, and we're sending it. We're continuously sharing all our information, all the transactions, but we're doing it in a slightly different way. But what does that mean for the network? Now, the current network is a peer-to-peer network, which I think this is a bad drawing, but it's a simplification. A lot of the nodes are connected to each other, and they're announcing everything that they get to each other continuously, the transactions. And then when the block comes, they send the whole block over, which is very expensive. When we get into phase 2 later this year, when we actually start connecting Teranode to the current network, we'll be in a hybrid mode because we'll have to listen on Teranode. We'll have to listen to that old P2P node. So we'll be more or less functioning in the same way, but Teranodes will be talking to each other on the back channels. They will start to do that. They will start sharing subtrees with each other. The SV nodes will not, but the Teranodes will, which gives them a benefit. If one of the Teranodes finds a block, it'll be instantly validated. And SV node will probably, take a long time to do that. And then we move into a completely Teranode world, where the transactions are coming in through something like IPv multicast. So we're ingesting these things very quickly. The Teranodes are all connected. They all have a connection on libp2p, which is basically, it's actually the library that's used by Ethereum. So we're grateful for those guys for helping us scale BSV. But we're sending out blocks, block announcements, subtree announcements, and objective transactions. So that's happening on the P2P. But the actual sending of the data, so the actual subtrees, and if you request transaction, the actual transaction data and the block data will be done in it. It won't be over the P2P network, it'll be through HTTP requests between the Teranodes. So we're moving into a slightly different network paradigm, but still fulfilling what says in the white paper that everybody shares everything with you. That's what honest nodes do. They share immediately everything they've got. They share with the rest of the network. And that was the presentation. I wanted to keep it short because we can go on this forever, but I wanted to give you guys an opportunity to ask some questions. So I think there must be lots of questions.
Okay, we have a question coming back here, but first, Connor.
What has been the biggest challenge you've faced so far, and what do you anticipate being the biggest challenge in the future?
I think the biggest challenge was in, like I mentioned earlier, you have this microservices architecture, and you have these services that are horizontally scalable. So, for instance, the propagation, transaction validation, the subtree validation, block validation, they can all be horizontally scaled. So, the current test, we have 26 nodes running on the propagation and validation. But they all need to talk to these shared services. So there's a massive amount of communication from all of them. So, and we had, so we're running all this in AWS, and there are some network limits on how these nodes can talk to each other on AWS that are kind of hard to find. The PPS, the packets per second limits and stuff like that. And we're hitting those, and we're having a lot of problems. We had to find ways of working around that. So what actually worked in the end was having all this communication batched. And we've done that in such a way that it's actually transparent. So services think they're talking to each other directly over gRPC. They're actually, all the communication is batched over. And that has reduced those network problems and basically allowed us to scale like this. The latest fix for the batching allowed MacBook M3 does 40,000 transactions a second on this one little because of this batching. So it's a shared services to each other and actually goes really well. So that's encouraging. That was the biggest pain points. Besides that, this has been called the impossible project, and there is a lot of things that can go wrong here, and it's actually to get this right. For the future, I think I like the unknown now. How we're actually going to get the transactions in here if we're going to do 1 million a second if we don't have IPv multicast, because the support for it at ISPs is not very good yet. And apparently, this is one of the first applications that would need it. The reason they say they haven't built it yet is because nobody actually needs it. We need it. So we have to start talking to AWS and Google and Microsoft, all these guys to actually multicast implement. We can use that. I think that's probably the hardest. A lot of the stuff, so we've kind of cracked it. Just to, I don't think I've seen it, but we're running now on a proof of concept, which means there's a lot of hardening that still needs to happen. Our error handling needs to be better. There's a lot of stuff that we need to do, but I think we've proved that a UTXO-based blockchain, proof of blockchain, can do 1 million a second. And in the proof of concept that we're actually running, we are actually doing all the work. Even if we might, there's some things that could be better, could be more optimized, could be faster. We are doing all the work, and it's working. Does that answer your question?
All right. And next question from anyone? All right, Ty, you will be next, and I have Mattia going.
Hi, CD. So I'm curious. Okay, when we get to the world of million transactions a second, it's a different beast. But in this transition, right now, for example, we're seeing sometimes miners that are primarily on something like BTC or BCH come into BSV. In that hybrid stage, is it possible that someone running SV node can still compete with Teranode in mining, and will they be able to even participate in the network?
Well, I mean, yes, up to a certain point, up to when SV node cannot handle it anymore. And I think we have to look at from an economic standpoint. I mean, if you have you're running a Raspberry Pi or you're running some server enabled, it doesn't matter what scale you run, but you will run into limits if you're not have something like this microservice architecture scales horizontally. You're going to run. Where are those limits? I think we talked about 20,000 SV node can do. 10,000. There's a number that SV node. If we go above that, the Teranodes will have no problem with it at all, but the SV node will. So the miner that's still running SV node will lose out on revenue. So it's an economic question. You should migrate, but we are working very hard on making them play nicely with each other, because this is a completely new node implementation, which has risks, right? So we don't fork the network, by accident and things like that. So we want to run side by side with SV nodes for as long as possible to make sure we're doing everything correctly. We're actually creating a valid blockchain together and all that. But at a certain moment, you just won't be able to keep up, and you'll have to switch to some miner. But I mean, in the coming year and a half, as a miner, I'd run both next to each other just to make sure. And if one of them has a problem, you can always the other one to mine. So.
All right, we have time for one more question, and this question is from Ty.
Just curious a little bit about trees and kind of the ordering, right? Because you've got a lot of them flying around, and they've got lists of TX IDs, and you blessed one sequentially. But are you doing any inter subtree like graph comparison to make sure that you don't have, say, one subtree that's a transaction, and then another one creates it afterwards, or something like that? I guess I'm curious just the ordering of these, and then if there's, and then how well does it tolerate miners that might have slightly different subtrees? Do we validate all the miners that we care about, or do we kind of agree on them and then choose to accept them as our own, or is that kind of not yet fully defined?
Yeah. We are basically, most of the subs are different because there's some jitter on works and then processing, things like that. So we're not getting the same subtree from miners. Just one transaction is in a slightly different order or something. The whole subtree is different. The subtree for us is different. So we validate all of them. So at the moment, we're running 6 node tests in a second. So each miner is getting 5 subtrees per second in to validate. And that will work. We validate. I think we're running 5 subtree validation nodes, small graviton machines with 6 GPUs. I mean, it's not crazy. And so all of them are validated. But what does validate mean? It basically means we've seen this transaction before. That's all what it means. It doesn't mean anything in order or anything like that. And so your question about the graph database, we looked into that. And graph databases are basically a implementation on top of another database. They're normally implemented on top of key value stores. So you're getting a lot of functionality. And it's actually very expensive processing because it's doing a lot of things that we don't need to do. It's doing things differently. It's not optimized for our use case. So some of the experiments that we did to use graph database, it didn't work. We couldn't get to 2 million transactions a second. So the first step that we do, just validate, have we seen this transaction? Yes, it's blessed. No, let's go get it. We'll process it, and it's blessed. The ordering problem that you're talking about comes in when we do the block validation. So somebody's actually mined a block. So it has proof work to that block. So you spend a lot of money on doing that. And at that moment, we load up all the subtrees into RAM, and we actually go through and see if the order is correct.
So there's a lot of caching strategies and stuff like that inside Teranode to actually make this work. Because if you need to do network calls, 600 million things, the performance will just die. So there's a lot of local data when we do that. But we actually check whether a transaction occurs twice in a block, not in a subset, in a whole block, so in the whole 600 million transactions. Is it there twice? And is the parent in there? And is the parent before that transaction and stuff like that? All the transactions that don't have a parent, we actually do a database lookup to see if it has been on the chain that you are. So we're kind of doing what you would do in a graph database, but we're bypassing the graph database. And we're doing those primitives directly on the key value store or on our cache data. Because that's what just wouldn't be fast enough. Does that answer your question? Okay, great.
All right. Thank you so much, Iggy. Excellent presentation. Thank you to everyone. Our speakers will be available for comment and discussion questions in our next room where we are going to be relocating. I want to thank everyone for being here, both in person and at home, for BSV DevCon. And what we're seeing is really the most significant paradigm shift and technological leap that we have experienced in all of human history. And the only thing I can think of that comes even close is the myth of Prometheus discovering fire. That's where we're at right now, and you know, the people that are tuning into this are the people who are going to have the fastest mechanism to take advantage of this new paradigm shift. We're going to revolutionize and change everything. And I want to thank you all for being a part of this journey. Thank you all to the viewers at home. If you enjoy this content, make sure you like, subscribe, share it with your friends. I'm your host, Brett Banfi, Manifestable. And thank you everyone for a really tremendous, wonderful BSV DevCon, and looking forward to a wonderful 3 days at London Blockchain Conference with you. And we can share the slides. The slides will be available online in the YouTube comments. Thank you, everyone.